hello, 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 hello. So actually, hello, 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 hello.
Put it on
Hello.
your lapel like it's supposed to.
Hello, 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 hello. One, two, check. Check one, two, one, two, check, one, two, check, check, one, two, check, check, one, two, check, 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 one, two, check, one, two, check, check, one, two, check, one, two, check, check, one, two, check, check,
Okay.
one, two, check.
Good morning, everyone. First of all, can everyone hear me? Is the microphone working? Excellent. All right, well, welcome to the 2023 edition of the Haskell Implementers Workshop. I am really hyped to be here right now and being able to run this thing, and so hopefully you are too. We've got an exciting lineup of talks today, but before we get into the talks, I have a couple of administrative things I want to go over real quick. So first and foremost, there's... Oh, okay. Is that possible to do on the microphone, or does that have to be done on that end? Okay, testing, 1, 2, 3. Is that better? Okay, well, I mean, it's important to get this right now because we're going to be passing this around and having this for audience questions, and we want to make sure that everyone can hear the audience. So, okay. I will try to speak into the microphone as closely as I can. And yeah, this is important because there is a virtual component to the Haskell Implementers Workshop. So we have a YouTube live stream in addition to being able to watch it in person. And you can go to the ICFP website where they have a list of all the rooms in this building. We're in the Grand Crescent room, so go there for the live stream. One slightly counterintuitive thing is I think YouTube live streams have a comment section, but they've told us not to leave comments there. Instead, you should leave comments on our Discord instance, which you can also find on the ICFP website. And there's a HIW channel specifically for the Haskell Implementers Workshop. There's also a specific thread for each individual talk that's going to be given at the workshop. So please do leave comments on the thread for the specific talk, and that way we can keep the discussion relatively self-contained, because otherwise Discord kind of becomes a blur of random comments and it's harder to follow. So we have someone here monitoring the live stream to make sure that things go okay video and audio-wise, but if you're watching this virtually and you notice any issues, please let us know and we'll try to get it fixed as soon as we can. Here's a really brief overview of what the schedule is going to be. This is, again, from the ICFP website. We're in the GHC status report session right now, and that's going to last until 10:30, and then we'll break. We'll come back at 11 for the first session of full-length talks, and that will last until 12:30, and then we break for lunch. We'll come back at 1400 for the second session. That goes until 15:30, and then finally we come back at 1600 for the last session. Note that the breaks and the lunch break are synchronized across all the different workshops. So like this schedule is basically the exact same as you would find at any other workshop. So when you break, you'll have time to mingle with people from other workshops as well. One thing that I'll ask for the presenters for the full-length talks who are going to be in each of the sessions 1 through 3, please come and test your device on this projector before the session in which you're slated to speak, and hopefully that way we can iron out any technical issues that might arise, because you never know what happens when you try to plug HDMI cables into laptops, and it's always a mess. So please test it out beforehand. So note that each session has a number of full-length talks, and these are going to be around 30 minutes in length, including questions. There's also going to be a number of lightning talks in each session as well, and that is the last thing I want to talk about. So one of the cool things about the Haskell Implementers Workshop is that you can sign up to give a lightning talk with relatively little overhead. All you have to do is go to this Google form, which is on the ICFP website under the HIW track. If you have a relatively self-contained idea, it doesn't need to be fully baked, but a self-contained idea about something that might be of interest to the people in the audience. Maybe you have some kind of work in progress development you want to show off. Maybe you have some problem that you think people in the audience would find interesting, or maybe you just want feedback or collaboration on some idea. A lightning talk is perfect for this. I asked that each lightning talk should aim to be around 10 minutes in length, maybe shorter if we get a bunch of lightning talks. We do have some slots still open for that, so it's not too late to submit one if you have something that you want to come up with a presentation for at the last second. One request I want to make of lightning talk speakers, if at all possible, send me a copy of your slides. The way I'd like to run it is to have all the slides from different Lightning Talk speakers queued up ahead of time before the session begins, and that way we can minimize the amount of downtime in between each Lightning Talk speaker. That might not always be possible, like maybe you have a live demo of some sort that you want to give. If that's the case, then it's fine to use your own device for that, but again, please do test out your device before the session begins if you want to do it that way. This is also a reminder to any Lightning Talk speakers who have already signed up, please send me your slides and we'll get things set up in the session before you're slated to talk. I think that covers that. Or is there any questions about sort of how that's run? Cool. Well, if not, then I want to hand it off briefly to Richard Eisenberg, the chair of the Haskell Foundation. He has a brief announcement to give, and then we'll hand things off to Simon, who's our first speaker.
Thanks, Ryan. I am chair of the board at Haskell Foundation. Some of you may have seen this on Discourse in the last week, but the current executive director of the Haskell Foundation, David Christensen, he has decided to take sort of an amazing opportunity over in Lean land to help develop Lean. This is something that really aligns with his interests, so he regretfully had to submit his resignation. So we are seeking a new executive director of the Haskell Foundation. I will be around all week, happy to answer questions about that or talk to you, but if you like the idea of sort of organizing us all and helping us to forge forward and make an even better language, that would be fantastic. Come talk to me. You can see our website is haskell.foundation, and then there's a button on the top. If you go to there, you can find careers for full job posting. That's it.
All right. Thank you, Richard. I'll go ahead and get things set up with you, Simon.
Okay, does this work? Yeah, more or less. All right, where's my little clicker thing? Okay, good. Keep forgetting about this. Well, good morning. I'm only 8 hours adrift, having arrived in Seattle at 6 o'clock last night. It's delightful to be here. As ever, in these kind of talks, I feel as if I am like the tip of an iceberg, the bit that sort of thrust briefly above the surface. But you are the body of the iceberg. You're all there sort of holding this up. So this is very much a sort of collaborative, interactive kind of talk. Maybe if I say things that you have something to say about, you can just contribute. So we have another microphone, do we? No, we do not have another microphone. No, this is the only microphone. Yeah? What was that? Yes, I'll repeat audience questions, but if you'd like to sort of contribute to anything, any feature or thing that I'm talking about, then stick your hand up and I'll just give you the microphone, right? So then we will all learn from each other. All right? So this is a brief summary of the state of affairs in GHC land. So here we are. Since the last ICFP, this is more or less trying to cover the last calendar year. Yeah. Oh, man. What is that? That's not my computer. My computer has no such background. And it's clearly saying, I can see what it's saying on this screen. Is it some mysterious mixing thing? Oh, that's your background, yes. Aha, how about just unplugging it? That would... Okay, well, I can see the slides anyway. and YouTube can see the slides, just that you can't. So I will read them to you until we. In the last calendar year, what releases have we had? In August last year, GHC 9.4.1, and since then there have been no fewer than 6 minor releases, kind of bug fix releases coming out since then. The last one, 9.4.7, was released just days ago, I think. Then 9.6 was released in March this year. Remember, we're on a kind of roughly 6-month cadence, and we've had 1 minor release since then. And 9.8 is on the, it's on the, what's the word, when they launch a ship, it sits on those blocks and then you cut the cables and it rolls into the sea. So Ben is about to cut the cables and roll it into the sea. October, we think, right? And 9.10 is already kind of in preparation. We're expecting to fork the tree in January. Now, here's a bit which it really would be quite nice to be able to see the screen. So you might wonder about these dates, like how do you get to know these dates? So people are asking that to us during the year. And so what we have got now is a GHC status page that I promise, show you, that says, I tell you what, I could plug my machine in instead of yours, couldn't I? Since it's displaying, it's HDMI cable, since we're displaying that, I could just move this over here and you can have it. What was that? It's not a laptop. Oh, right into the projector. Oh, look. Just holding it in the air did the job. Or else you did something. Or maybe you did something. Or maybe it was just holding it in the air. So here is the here's the GHC status page, which from now on we promise will be kept remorselessly up to date. So here it is. It should be easy to find. I'll show you how to find it. But it says here, what are the next planned release? What is the status page for each? And if you follow this percent thing, is the GitLab notation for milestone. And if you follow this link, you'll get to a little page. Here's the one for 9.8.1 that gives the schedule, including all the alpha releases and release candidates and so forth. So that should mean that on any day you can find out what the status of all releases is in. And there's quite a bit more on this page below. Down here, scroll down, there's quite a bit more. Search for GHC status page, you'll find it. Okay, so far so good. Now, 9.6, so here's a quick roundup of what's in the compilers that we've released since this time last year. 9.6, what was in 9.6? Delimited continuations. This is the big one. So Alexis, just tell us briefly about delimited continuations. You've got some text here to support you.
Yeah,
I really warn you.
I've already included an entire talk on delimited continuation, so this will not be quite as long as that. But basically, we have these 2 primitive operations for capturing the continuation. They're very simple. It would be great for people to use them. Let's see. I guess, so the way that currently we handle things is very naive. And it seems to perform pretty well. So I think kind of the plan was we would implement things in a very simple way, and then hopefully people will give us bug reports. And so far, I don't think we've received any bug reports, but it would be great to get bug reports. But yeah, use them.
But it's the pathway to, among other things, efficient effect handlers, right? Is this still working? Hello? Yeah, it is? Okay. All right. So for me, this is a big piece of sort of... big step forward, qualitatively new thing that GHC hasn't had until recently. Okay, here's a smaller but useful thing. When you declare a data type, all the data constructors can be made available as types. Remember, like this is called data kinds, isn't it? But Yavor has been long arguing, saying you should be able to, when you declare a data type, to say I want it only to be available at the type level. And I don't want to put those funny tick marks in front of the data constructor names. This is a sort of namespacing thing. So this is a small quality of life improvement. You will notice in this talk that lots of these slides have a URL at the top. The slides will be available afterwards. A lot of this is being driven by the GHC proposals process. Right? This is Yavor's proposal. And likewise, here's Alexis's one, which is the result, by the way, of a lot of work. There was many iterations of that proposal. Okay. Anything else to say here? Yeah. Right.
One clarification here is that Yavor, I think, originally proposed this idea, or is one of the original proposers, but Ross Patterson was a person who actually implemented this. So I think most of the credit goes to Ross for actually like pushing this into GHC itself.
I'd forgotten that. I just naively took the author of the proposal. So thanks. Good. Here's another small quality of life improvement. When you do an update of a record that contains existentials, which sounds exotic, but people do it, right? Then what is going to happen? Well, so here's a record which contains an existential. Look, it's got this existential field A that doesn't, or type variable A, that does not show up in the result type, right? So if you're going to update this record, you must simultaneously update flood1 and flood2 with mutually compatible values. Does that make sense? Right? And so for the longest time, GHC couldn't really do this because I was heroically trying to type check the original program that the programmer wrote, right? And rather than, say, first desugaring it into the case expression that it stands for and then type checking that. But that became insupportably complicated. It's really quite hard to type check this directly. It's just easier to desugar it first and then type check it. But for a long time, we have not wanted to. Have I got a second slide for this? Yes. We've not wanted to do that because you get worse error messages. So this is a little tip of the iceberg thing that says that now for some constructs we are desugaring them before type checking, but we are also keeping track in the implementation of the old pre-desugared thing. And we are careful in type checker error messages, there's a systematic way of doing this, to make sure that we never mention bits of syntax tree that were not in the original program. Does that make sense? So, as it were, the desugared program has bits of syntax tree that come from the desugaring, and then you get back to old stuff that was part of the original tree, and the source location information keeps track of which is which. So I think we're going to see much more of this. Apurva, where are you? He was here. He's in another room, right. So we're going to do this for do notation, but there are quite a few open bugs about do notation and applicative do that essentially amount to the same thing, that it was too complicated to get, particularly in combination with rebindable syntax, right? So it's hard to get all these moving parts to work together. So now we're just going to do more desugaring in advance with careful attention to maintaining good error messages. I think it's good plan. So, but Carrie MY, who I've never met in person, you're not here, are you, Carrie MY? No? Heroically did this for records. Okay? But watch out for this, because I think this will be, you'll see more of this. Indeed, you may get involved in doing some of it yourself. Loiter and Cheng have heroically been working on backends for WebAssembly and JavaScript, respectively. So, Loiter, do you want to say anything about this?
Well, I can't claim all the credit since Jeff and Josh have been doing lots of the work. But this has been a fairly long-going project known as GHCDS for a while, but it's been very hard to keep up with the change of progress of GHC that's been increasing, and I'm happy that we are getting closer to having it less non-standard, just having a different cross-compilation backend. And a lot of things had to be changed to make GHC more cross-compilation friendly, and I'm very happy that we're getting there. It's still not quite to the point of feature things. We still need to work on an optimizer, and template Haskell has landed very recently. But that's pretty much it. I hope everyone will try it out.
Yeah, there's a long saga here, right? And it's not done, right? So I put here by no means done, and full of volunteers needed. So I think people will be very happy to. So Anil.
Which version of WebAssembly are you targeting for the Haskell backend?
Which version of WebAssembly? So this is really Cheng's question, but Cheng isn't here, I think.
It's the MVP, the so-called MVP of WebAssembly. So right now, the next WebAssembly will include a garbage collector and all these things, but we assumed a much simpler WebAssembly, only the MVP. Yeah.
So I think this. I have a feeling it's kind of like there's something viable is working, but I feel as if the first 10% has been done. There's quite a long way to go here, but it's pretty exciting. Okay. What next? So more compiler and runtime system quality of life improvement. So one thing is that, actually, this was a customer, wasn't it? Someone who uses GHC was finding that template Haskell was very slow. And why was it slow? It was because it was linking. When you run a template Haskell splice, you have to run code that's in some other module. How do you do that? Well, you link the other module, and the linking process turned out to be slow. So this prefer bytecode flag instead looks in the interface file, which we have, which of course you must have loaded already in order to use that module at all. And in the interface file is all of the core for that module, and we can compile that core to bytecode on the fly, right? And that, surprisingly, is a lot quicker than linking. I don't know why that is. Ben just looked at me and he said, "It's just slow, Simon." Anyway, it's but the result, this is pretty significant, right? Compiling 40% faster makes a big difference in people's lives. Let's see. Who already knows what info table provenance is? See, okay, about 20% maybe. So I'm going to tell you, because Ben had to educate me about this last night as well. So whenever you allocate a closure in code, like say in your code you say let f equals lambda x blah blah blah, a local function definition, or a thunk let x equal y plus 1, then you're going to build you're going to allocate at runtime a little closure that contains the free variables and a code pointer. The code pointer, of course, points to the code to evaluate that closure, but it also has information that describes the layout of the closure and stuff like that. It's metadata. But it can also include a pointer that says, well, that closure came from this piece of source code, right? It's sort of statically related. So that's called the provenance of the info. The info table is the metadata. The provenance of the info table is which bit of source code allocated it. Right, that's good. But what happens if it's a constructor? Like you say, let x equal y cons y's locally in the body of a function definition. Well, a cons cell, back in the days when we were just thinking about cons, in the original design, a cons cell, its info pointer, its code pointer in the closure, it's still got a little heap allocated closure. It just points to a single fixed cons cell, which of course tells you nothing about which particular cons cell allocation site gave birth to it. Right? So the trick is simple. Just make a new copy of that cons info table, one for each allocation site. And of course that makes your binary bigger, but it means when you're crawling over the heap, and Ben spends his life crawling over the heap, then you can say, oh, that cons cell was allocated right there, and that can make a big difference. So that's been in GHC since 9.4, 9.2, something like that. These changes here are to reduce the overheads, right? So the costs, the static costs of capturing all this extra provenance information, and they make quite a big difference, right? So,
and to clarify, this was also a sort of client project that WellType undertook because they were our client wanted to ship this to their binaries with IP information to their clients in production code. And you ship a 500 megabyte binary to your clients, they tend not to be very happy. So we're slowly chipping away at this.
Production code never crashes, so why would you need this? Okay, I'll pretend I didn't answer that question. And also, this is also credit to Ben and WellType's customers, I think, pause time improvements in the non-moving garbage collection. So the non-moving garbage collects incrementally with the game of reducing pause times, and you have substantially reduced pause times. Yes. Yeah, that's in 9.6. Yeah. Okay, so good improvements. Error codes. Who knows about error codes? Hands up if you already know about error codes. Okay, so maybe close to the majority. So just a reminder that we're moving from error strings, this is the compiler produced errors, from strings to a data type, and moreover, every constructor of the data type, or every distinct error within it, has a distinct error code. Why is it good to have a code, an actual number? Well, it means you can look it up in the Haskell error index. So this is a Haskell Foundation project. This I did show you last year. Here's an example of the error index. It's got lots of GHC error things here and a summary of what it means. Of course, you can Google for the error number. That's good, right? Much more greppable than the grepping for the string. Much more Googleable, and you get a page of description about what it is and how it might arise and how to fix it. Of course, I don't think we've got write-ups for every error by any means. So this is another thing that you could do, is to pick some errors and to add to the Haskell error index, which is it's not even part of the GHC repo. And the last thing to say about the error index is it isn't just GHC, right? This error index is covering GHC up and stack, and here at the bottom are a few GHC up and error messages. So if you're a user of Cabal or stack or GHC up, and you come across an error, you think, finally I figured out what it means, can you submit a pull request to the error index for them too? Right? And they're distinguished, as you can see, by the prefix S and GHC up and GHC. Okay? So I think this is pretty, in the big scheme of things, this is a fairly big deal. Seems mundane, but actually the aggregate effect of all these little snowflakes is significant. Did I miss anything here? Yeah, no, nothing. Okay? All right. So that's 9.6. That was only 6 months, right? So 9.8. What's in 9.8? This is a personal favorite. Yaro's not here, is he? No. So have a look at this quote from Duncan Coutts's thesis, right? The most significant remaining practical work on stream fusion is to resolve the problem with effectively optimizing uses of concat-map. So this is like by the way, this is 2010, so this is like a 15-year-old, more than 15-year-old problem with fusion, right? Called the concat-map problem. And here it is. The rewrite rule that we want says concat-map applied to lambda x stream next f of x rewrites to concat-map prime of that next there, and that f. Oh, that f. Ooh. That f is a function, right? So in a use like, what we'd like to write, I mean, syntactically is no problem. Here it is, visualized in GHC syntax. Here's a rewrite rule. Concat-map lambda x stream next f of x. Oh, and by the way, it's quantified for all next and for all f's. Right? Not for all x, because x is bound here. But the idea is we're going to match the left-hand side, get bindings for next and f, and then spit out the right-hand side as the optimized thing. And this one line of code is the thing that makes stream fusion work nicely. Okay? And we haven't been able to do it. And why haven't we been able to do it? Because it means matching to get a binding for a function f. So if I have something like this, lambda, if I have a call, concat-map lambda x stream next g of x plus 1. Oh, that doesn't look like f of x, right? Look, it looks like g of x plus 1. That's not f of x. But of course it could be if I chose a suitable f. The f that I want is lambda x g of x plus 1. So, we've known about this for some time, and we thought, that means high order matching. And you look at papers on high order matching and they make you want to lose the will to live. And it's undecidable and it's all bad. So I've always just taken this as being, gospel, that you can't do high order matching in a tractable way. And Yarrow said, but Simon, look, here's an implementation. I said, Yarrow, it can't be done. And and we went to and fro like this for a bit. And after a bit I thought, he has a point. And it turns out that he'd identified a little sort of subcase that can be done rather well and very easily that was not really documented properly in the literature. You could, if you looked at some past papers with the right kind of eyes, you could see that it was there. The people who wrote these papers knew about this. But there's a little case that says if you've got this expression here, right? So in the pattern, there's the pattern, and it consists of a pattern variable, f, here, for all f, applied to what? Well, I beg your pardon. It's an expression whose only free variables are one of these template variables and a bunch of locally bound variables like x. And you'll have to read the user manual to see the exact rules. I'm not going to drag you through them now. But the point is there is a very tractable subcase of higher order matching that is just powerful enough to do this. So the reason I made a bit of a meal of this point is because Yarrow implemented this. It's in GHC 9.8, but it's been like throwing a stone into a pond. I expected there to be tidal waves of enthusiasm and people building new libraries with clever rewrite rules, but no, nothing. So guys, this is amazing. Try using it. Okay? All right. Custom warnings. This is again about quality of life for users here. This is saying, look, instead of, at the moment you can say, you can get a warning if you use head, right? But that's a warning that you can either switch off all warnings or no warnings. So you don't want to switch them all off. So it's a way of categorizing warnings so that you can write something like this that says, oh, I'm creating the category X-partial, and then in your, let's see, in your invocation line, you can say, please warn me on X-partial warnings, or please suppress X-partial warnings, right? So you could just divide your warnings into categories. So it's something that library designers can use to control to allow you control over what warnings you get or don't get from their libraries. Okay, I think it's quite right. In the same spirit of controlling warnings, deprecated exports. So here, this function lines is here being exported, re-exported from data.list. It's not actually defined in data.list, and it's a perfectly respectable function, defined in some module and exported from there. But data.list is re-exporting it. And this deprecated pragma says, please don't import data lines from data.list. Instead, get it from data.string. Okay? So for whatever reason, but the point is you couldn't do this before. You could either deprecate lines entirely for all users, which is not good because lines is a perfectly good function. This allows you to deprecate the place that it's imported from, which allows you to transition module structure, right, when you change the structure of your modules. Okay. So, yep, another GHC proposal. Unsatisfiable constraints. This is to do with when you want to have user level or library level control over type error messages. So again, you go and read the initial proposal, but I've take this one here. If you've got an equality instance for A arrow B, well, one possibility is to just say, do not provide an equality instance for A arrow B because you can't take equality of functions. But then GHC says no instance for A arrow B. Now, for equality on functions, you might say it's obvious enough, but if it's a domain-specific library and they say no instance for C of T of A, then you think, why isn't there an instance for C of T of A, right? But so this way you can get a decent error message. This says, oh yes, GHC thinks, fine, I've got an instance for EQ of A arrow B, and here it is. It says, oh, but to do that, I've got to prove unsatisfiable, and it can never prove unsatisfiable. Instead, it just prints out the message. And what is the message in this case? Well, you can make a message that says something like, don't use the equality instance for arrows because you can't compare functions for equality. Does that make sense? So it's about domain-specific error messages. And you can do it not only for instance declarations, but also for functions that you couldn't call. The proposal has quite a few more examples. It doesn't give you any new expressiveness. It gives library designers new ways to offer feedback to their clients. Okay? All right. Many of you will know that there's been a long strand of work on dependent Haskell, and it can be quite difficult to keep track of it because there's quite a lot of moving parts. So in this slide, I've just tried to summarize where things are at. So particularly, I suggest you look at this stage. Look, here's the URL, and here's a status page, which I use myself for keeping track of what the moving parts are. And it also has a pointer to the overall design plan, right, that says, what are we trying to do? How far are we trying to go? Because dependent types is not one destination in language design space. It's a whole little sub-universe of destinations. And it's easy to get confused, and it's easy for people to talk past each other because you think you're actually talking about different things in the destination space. So this design for dependent type says where we're heading. It's a GHC proposal itself. And this status page keeps track of where we are on implementing it. I think at the moment we're quite a lot in the stage of doing consolidation. Here is a consolidation thing that's in 9.8. You'll know that in a function call or in a type, you can use visible type applications, which means you can say f at t XYZ, meaning call f instantiating its first type argument to t. That's called visible type application. It's been in GHC for quite a while. But what we haven't had is visible type abstraction, right? So here is a data type t. It's got a separate kind signature, which has been in GHC since 9.2, standalone kind signature. So this is saying that the type constructor T has kind for all k, k2, for all j, blah, blah, blah. And now for the first time with this change, again, a GHC proposal, you can explicitly bind the k in the data type declaration itself. Right? So here I want to say, in the data type declaration, I want to say A as kind k, but where did k get bound? Previously it was bound by a sort of implicit binding mechanism on the left-hand side. It was never terribly satisfactory. Now we can just bind it absolutely explicitly here and here. Does that make sense? So I see this as being kind of like filling out the design space, right? That as soon as we got all this kind polymorphism, of course you would want ways to say this kind of stuff, and we didn't really have it before. So it was got it implicitly there, and now it's explicitly there. It doesn't add it directly any new expressiveness. There is one breaking change that I want to bring your attention to, which has been a wart on the language that I have hated for a long time. If you declare a type synonym, just an ordinary old Haskell 98, well, not Haskell 98, type synonym, and you say type T1 equals nothing with kind maybe A. What does that mean? Where is A bound? A's not really in scope there, right? So up to now, GHC has had some magical mechanism that says, well, look at the right-hand side, and if there are any kind variables that are not already in scope, then pretend that you bound them on the left-hand side. Right? It would be better, a better principle would be to say variables mentioned on the right should be bound on the left. I mean, if I said type T of A equals A arrow B, you would say, what are you smoking, Simon? Right? You got a B on the right and no B on the left. That would be bad. And so now you can say A on the left, and you must. I forget exactly about the sort of deprecation plan for this, but now the idea is things mentioned on the right should be bound on the left. Right? And this is the way God intended this to be done, essentially. And we were sinning before. So it's part of, and these things cause a lot of pain and angst because we have to think, how are we going to break people's programming and how are we going to have proper deprecation cycles? Pay a lot of attention to this stuff nowadays, but at the same time, it does seem important eventually to get to a destination that you can defend rather than this kind of nonsense. Okay? Anybody got any questions about, do I want to say anything else about dependent Haskell? No. Because I know that this is territory in which there's quite a lot of discussion some of the time, but I think it's moving slowly but steadily and quite conservatively, actually, in the right direction. Anybody want to add anything to that? Richard, you got anything to add? No? All good? You're being terribly quiet, This is not really a sort of Haskell-y audience. Maybe it's because it's all so uncontroversial. Maybe I should try to say something more controversial. Okay. This one I don't... Ben, why don't you describe this one? Because I've been talking enough.
Sure. So this is a long-standing sort of low-hanging fruit when it comes to improving compiler time. Typically, you're not compiling just one Haskell library or one program. You're rather compiling a whole suite of packages. You're using a program such as Stack or Cabal to do so. And up until now, we've not really had a great way to allow you to use the full extent of your machine's parallelism that you have available. Yeah, you have 64 cores now for a few $1,000s. So why can't we use that parallelism? Well, because it's complicated. But now we actually can, right? So we have this ability in GHC to be able to use this mechanism, which we called parallelism semaphores, allowing multiple GHC processes and, in fact, multiple compilers in general. This is a very there are linkers and some C compilers also support this. Make does as well, similar mechanisms to allow compilers within a build, a multi-language build even, to distribute work among cores and ensure that you don't oversaturate the machine. And this actually can allow you to not only, up until today, you typically have had to be very conservative in how much parallelism you allow, for instance, Cabal to use. Now you can actually tell Cabal, use my machine to the extent you can use it, and you'll actually get a rather remarkable speed up in many cases. So here we see almost 50% speed up on a fairly typical build plan and system. So hopefully this will help. Let's
do a quick tutorial on how it works. So if you're Cabal, right, and then I'm one copy of GHC that you've invoked, and Alexi is another copy of GHC that you've invoked, and Richard is another copy of GHC, and you've invoked all of us, right? Then we each, and then your cabal, right? And then Ryan is the parallelism semaphore thing. Is that right? Cabalism. Okay. And so, as one copy of GHC, I can then, if I want to start up multiple parallel threads to compile lots of modules in parallel, which I can, but I'm really GHC --make. Then I ask Ben again for permission. I say, could I have another token to create a thread? You say, yes, Simon, be my guest. And you hand out several. And then Alexei comes to me and says, could I have something? Ben says, no, Simon's got them all now. But then I have to give some of them back, and then you could hand them to Alexei. But the idea is that Ben never hands out more than 64. Right? Yeah. So there's kind of one central manager for permissions to spawn a thread. And all the separate GHCs or cabals or linkers communicate with the central manager in the same way. Yeah. So that's kind of cool. And again, it makes a difference in real life. And that's what we're trying to do. Okay. Tell us about snapshots.
Yes, so this is the first step in our long-standing plans to finally get some sort of form of backtraces in Haskell. In particular, you might have heard, and you will hear about this exception backtrace proposal. This is sort of the first step in that direction. So in order to offer a stack trace to the user, of course, you need to have some way to capture the state of the stack. And this is something that Sven Tenney was working on, and we managed to land for 9.6. We now have first-class ability to take the current state of the stack and freeze it on the heap, allowing the program to continue running potentially, but then have a persistent copy of the stack as it was captured, and then be able to later in 9.10, as we'll see, we'll be able to actually decode these stack snapshots into sort of human-readable stack traces, and that will go nicely with some future work that we'll also hear about in just a bit.
Thanks. Ryan, yeah.
Stupid question. How does that compare to the backtrace you get if you compile with -p-prof?
That's a very good question. Let's address that. Okay. Yes. So actually, as we'll see, the exception backtrace proposal has several different mechanisms for collecting stacks. This is just one, but I suspect this is probably going to be the most widely used one. Profiling is something that is great for a debugger, diagnosing performance issues. It's not so great for deploying to production because of the overhead involved and the fact that profiling ultimately is going to affect simplification and therefore the optimization available to the compiler when compiling your program. And there's quite a few there are at least two other mechanisms as well, in addition to profiling. You have has-call stack, which we've had for quite some time, and also the dwarf native backtraces. But all of these have various trade-offs. I suspect among the four options that we have, this native, what I've called a native stack, Haskell stack trace functionality is probably the most suitable to production use. It gives you sort of the best detail while having essentially no runtime overhead and not affecting the optimization of your program. So
Typically you'll grab a snapshot when something has gone wrong.
That's right.
Yeah.
Yeah.
So until then, nothing has changed to execution. Yeah. So yeah. Thanks. Well, I think you were going to say a bit more about that shortly. Right? Yeah. Okay. Fine. Right. Last thing I think from 9.8 is this is a proposal about extended literals. So we've got lots more data types, of fixed widths, int and word, widths of 8 and 16 and 32 bits, and now we can write literals of those types as well. So too. You would think that Sylvain, I think, made the proposal, and I think did the implementation as far as I remember. But I do want to stress that every release, including 9.8, has a lot of groundwork going on. There's bug fixes, there's optimization improvements, there's improvements to the debugging and performance and testing infrastructure. It's just like I feel as if I sit under sort of fire hose of code reviews and often bug fixing in the type checker or in the optimizer. And if the optimizer gets a little bit better in some cases, that isn't like a feature that I would tell you about here. And yet collectively, they make a difference. And lots of people contribute to those kind of things. So as well as these sort of visible, again, these bits are the visible bits that poke above the surface. There's quite a lot more underneath done by unsung heroes, many of whom are in the room. Okay, quick look at what's happening in 9.10. So this will be shorter. So 9.10, the idea is we're going to fork the tree in around about January, with a release expected around about March or so. Yeah. I think probably we're not expecting a lot of big new things on the language front. We might finally get all patterns, and a little bit more progress on various things here. Type template Haskell and unlifted bindings. Oh, the whole unlifted data type stuff is a gift that keeps on giving. GHC gradually keeps getting, slightly dealing with unlifted data types slightly better. More on cross compilation. So, do you want to tell us something about cross compilation, Ben? So this is another.
There's a lot to say here, but I will try to keep it brief. Right. So ultimately, the point here is that we now have several platforms that we support, WASM, JavaScript, and increasingly ARM, which is really, and RISC-V for that matter, yep, that often you don't see on a developer's desktop, and so, but you still need to produce code for these platforms, and so ultimately we need some way to be able to provide a first-class experience to developers who want to run their compiler on their Apple or their desktop machine, but then produce code for other platforms. Of course, we have supported cross-compilation for quite some time now, but it's long been sort of second class. It's inconvenient. You need to download or build a second binary distribution. Whereas other languages have shown that you can actually have really great developer experiences in a cross-compiled setting. In the case of Rust, they've shown that you really can. It's a matter of just Rust up, add a target for x86-64 or ARH64, and all of a sudden, 30 seconds later, you'll be able to build code for ARH64. We want to offer a similar experience if we can, especially given the prevalence increasingly of WASM and JavaScript. And so this work that our intern at WellTyped, Rodrigo, did over the summer is just the next step in that. This is, of course, something that Loyota and the team at IOG have also been making really great strides in. But generalizing GHC to be a compiler, which you can just say at runtime, GHC -target, or compile time rather, GHC -target, ARH64. And all of a sudden out will pop ARH64 code, and then integrate that into GHC up and Cabal and all of the tooling that one would expect to be able to provide a really great experience for users of the compiler. Does that answer? Okay.
I love to see it happening, but I haven't got a clue about how to do it or why it's so hard. But just tell us about diagnostics as JSON as well.
Oh, that's right. Yes. Let's see here. Right. So this is work that has been going off. Boy, this was a HF proposal actually. For a long time, users have been asking for sort of more structured output from GHC, the ability to get errors as structured documents that maybe not. Increasingly, users are using HLS, but still there's space for the sort of the lighter weight editor plugins and such that you can really that can find use in more structured output from the compiler that does not require linking against the GHC library, and so. We've long had this dedump JSON flag, which will kind of approximate this, but was never really first class. It was always never well documented and never stabilized. So Ben Belloc has been putting effort into trying to come up with a really defensible mechanism where we can say, this is the format that we will produce, this is how we are going to evolve it going forward, and this is how end users can use it in their integrations with GHC.
As someone who's never really used RISC-V much in practice, is there like a particular use case that is motivating a RISC-V backend? Is there something that's driving that work?
At the moment, I think it's primarily interest. These are Sven and Moritz. I don't know their individual motivations, but I think it is. I think this is going to be an architecture that we'll see more and more, especially in sort of embedded or settings, and we'll have to see. But it's certainly helpful to have GHC run in more places. Yeah. Let's see. What do we have? Yeah. All right. Yes, we have been focusing a lot on profiling recently. So this is something that work that has been sponsored by a client of ours, developing various tools to help them understand why their program is slow, why their program is looping, why their program, all of the sort of pathologies that you typically find in a Haskell program. We're one by one sort of picking out the top of the list and developing tools to help them understand those problems and avoid them. So in 9.10, we're going to have one feature, this orig thunk info. So in particular, it's very common that you'll find in your Haskell program, you write, let x equals x somewhere in your program, and you try to enter x, and all of a sudden you get a loop error, right? And that's not very helpful. That's really really, yes, exactly. Where did I go wrong? And this is something that's actually very difficult to debug because in general, these problems can actually manifest in rather large heaps, which are rather hard to disentangle after you've entered, because the actual thunk that you entered is actually been overwritten by a black hole by the time you find out that you've looped. So you've actually lost the information necessary to identify the culprit in many cases. This feature, orig thunk info, is essentially adds instrumentation to the compiler, which allows at runtime to examine the heap and sort out, oh, well, it was this thunk x in my original program that I entered that is inducing this loop. This is something that we found very, very useful in debugging, again, a client issue, and I think we'll find uses in our users, for other users as well. Was that? Thank you. Okay. Right. In addition, we're going to get heap profiling support in non-moving GC. This is actually great because this is a bit of non-moving GC work that I am actually not responsible for. So Teo, our contributor, has been working increasingly on the non-moving GC, as he's found his employer has been finding it increasingly useful. So it's now gaining heap profiling support. We're getting more flexibility in info table profiling and info table provenance emission. So as Simon described earlier, we've long had, for several releases now, had this info table provenance mechanism, and increasingly users are wanting to ship this information to their users. But for a variety of reasons, either because of binary size or because of runtime overhead that this distinct constructor tables mechanism that Simon alluded to earlier incurs, we don't want to go whole hog in the direction of sort of emitting this info table provenance information. We want to be a little bit more surgical in where we emit this information and which distinctions, how much we let it affect code generation. So we're sort of growing, GHC is growing more knobs to allow the user to be more explicit about what information they want out of their info table provenance. Further, we have further improvements in the non-moving garbage collector, further pause improvements. As I mentioned earlier, Sven in 9.10 has implemented stack snapshot decoding. So this is, again, in service of this exception backtrace proposal that's been sort of long on the verge of being merged, but I think in 9.10 it's actually going to happen. We're making great strides in getting the proposals through, and I think we have a really great design at this point. I'm very happy with how we now, what started off in this proposal as a very sort of niche, let's just tack on a backtrace to in some exception type, now is sort of blossomed into a far more generalizable, general purpose mechanism for annotating metadata on exceptions. And I think, I hope you'll find it useful well beyond just simple backtraces. We may be getting an IOU ring based IO manager for Linux. This helps scalability in many server applications. And of course, there's anything that you might be working on. So I'm not sure. I think these are just the sort of things that we've been focusing on. But ultimately, there are many people in this room who are no doubt have things of their own that they'd like to see in 9.10. So please, let's hear. Nobody, not a single. There we are. Okay.
I am, but it's a small thing that's been going on for a while. It's related to linear types, as everything I've been doing in the past few years, and so currently, when you write a let expression in with linear types, it's not going to be understood as something binding linear variables, which is immensely silly and absolutely terrible UX, and I apologize. And I thought it would be an easy fix. After all, having case understand linear types was a one-line fix at some point. And so linear lets took me like a year, basically, to like 1 day a week at a time. But it's been it's been a long road to fix all the paths that were involved in type checking lets. It's currently a merge request that I need to fix a few things for. But it's going to land way before 9.10 cutoff. So this one is going to be in.
Oh, there we go. Jeff?
Hello, I'm Jeff. I work at IMG with Leita and Josh. I wanted to point out two things. We had an intern, Bartek, who did the export deprecation implementation. And what was the other one? I mentored him. I should know this. And the instance deprecation implementation that, and I wanted to congratulate him on a successful internship. And he also had, I think, more robust warnings for record wildcards. That was one. The second thing I wanted to point out was I have a merge request, like all of you in this room, that is in flight and is so close to being merged. But what it does was add the links to the Haskell error message index to the error codes, and all I need to do is check that the terminal is smart enough. All the other logic is done, and most of the effort was not actually on the implementation. It was fixing the CI test suite to not completely melt down when it sees links. So please search for this on GitLab, and then please contribute, because I do not have time to work on it anymore. Thank you. Yes, that is a healthier and better way to say that. Yes.
Is there any work, the JavaScript land, things that we didn't cover in the...
So in JavaScript land, we are missing the optimizer that was in GHC.js, and the reason for that is that, according to Leita, it tried to do too much and was a buggy mess and was not maintainable. So the current plan there is to revise the IR that we compile STG into so that we actually have a good optimization target. And that also is very close to being done, but I have not had time to really land it, and there's a bug we have to work on, or we're going to pair program on this week. So you want to add anything, Leita?
I don't think it's close to being done, but we're working on it.
So I'm going to sneak in here some Cabal and Hackage updates as well. Not coming in 9.10, but things that have already happened. And in Cabal land, it's largely been incremental improvements in stability. The one new real headline feature is that there's now the haddock-project command. So if you've got a project with many different packages that are all like sort of depending on each other, you can run Cabal haddock-project, and it'll generate haddocks for all of that stuff, all hyperlinked together, to get you nice local documentation for the whole project at once. Also, just like GHC has error codes and Stack has error codes, Cabal error codes are now underway with our Haskell Summer of Code, and are going to be getting added to the index, and we'll be filling those out too. And so we're going to get better structured error messages for Cabal. And then on Hackage, hopefully some of you have already noticed this, but it is new since the last in the last year. So the big headline feature is there are reverse dependencies directly on Hackage, and you can follow through and trace the chain of all of those. And along with that, less noticeable, but I really encourage people to use if you're interested, is we've got a very rich now notification set of features that you can turn on. We didn't turn them on for maintainers by default because we don't want to spam you, but you can go to your account settings and turn on all these email notifications that will let you know, for example, if a dependency is updated in such a way that it breaks the bounds on a package that you are maintaining. You'll get an email about that. If there's a metadata update made to a package you are maintaining, you will get an email about that if you opt in. And a variety of other useful things for maintainers to know. Also, if you upload a package and the builder tries to build it and it fails, you will get an email about that if you opt in. So please do opt in, try out the emails, and see which settings are useful to help you manage your hackage packages better. Oh, yes, and the one more thing. These have existed and for a long time, but only in the last year have they moved out of experimental so that you can upload to hackage a package with multiple exposed public libraries. We have in flight the work that they won't display very well. They'll only see the haddocks for one. We're going to fix that. But now you can upload and experiment with them and depend on them, and they're fully supported and in every other way. So if you've had like a whole bunch of packages that you thought these should really just be multiple libraries exposed from the same package because they all move in lockstep for whatever reason, and there's a bunch of use cases I won't go into, you can try that out now and start really doing that in earnest.
Excellent. Is there going to be a blog post or something about the notifications work? I was actually unaware of that as well. Okay.
I was just saying we did announce it on, but just on the discourse. We haven't been very vocal about this, so yeah.
Actually, Finley, you've been doing work on Haddock, right, and improving performance of Haddock. Do you want to talk about that at all, or? Yeah.
Yeah. For well-typed, I was doing work on reducing the memory usage of Haddock and making, landing high Haddock is like the biggest thing in this work where documentation gets generated from interface files. And so along with that, you get like recompilation avoidance in GHC, so you can avoid recompiling your project just to generate documentation. And currently working on the Cabal feature that also would help Cabal not trigger that recompilation. So yeah, Haddock was going to perform much better in future releases, and hopefully we will have easier recompilation avoidance during documentation generation. So.
All right. Do we have, okay.
Which was that clearly the hackage-rich notifications were pushed forward as a hackage notification, but nobody was opted in, so nobody heard of it.
Anyone else? Oh, there we are. Yep.
I mean, I feel like I'm cheating a little bit because Simon mentioned all of this amazing work that people are doing on making serializable errors and all of this stuff, because it used to be that GHC IDE would actually figure out what error you had by doing regexes, right? And it would extract names out of them and things like this. And now we've got structured errors. But so what I've been working on, and there'll be a talk about it in an hour or so. Essentially, it's a post-processing plugin for specifically so that you can rewrite type checking error messages for when unsatisfiable fails you, when it's not sophisticated enough, when your DSL just has some type machinery inside of it that is just too dang good to expose to the person who's actually using the surface level DSL. The hope is that you could use this post-processing mechanism. There's a few other uses for it. Maybe I shouldn't spoil the entire talk right now. So yeah, I'll just leave that to later.
Excellent. All right. Anything else? Okay.
Let's move on. There's a couple more things I want to cover before we finish. So one thing is just to talk briefly about the role of the Haskell Foundation and what's happened in the last year. So you remember I put up a slide that's more or less like this time last year, which is to say Foundation's been really helpful to GHC land for improving coordination across the ecosystem. I put up some particular points here, but we have had material improvements in this coordination, right? We're actually holding regular meetings with our stakeholder compatriots in other parts of the ecosystem, like the Stack folk, the Hackage folk, the Cabal folk, and GHC Up, and HLS, right? Ben spends a lot of time in these meetings, I think. But these have tangibly resulted in some changes, right? So now when GHC comes out, GHC Up is out the same day or later that day with the new release of GHC. And HLS is not far behind. And we're working much harder on getting the GHC Up you get isn't a sort of postfix on GHC. We've actually tested the release with GHC Up before as part of CI. So this all makes a difference. So that's in general. I wanted to give you two other specific examples of things that have happened this year. One is that David, under the auspices of the Haskell Foundation, did a kind of survey of a selected group of Haskell users. It wasn't an open thing, but he chose a reasonably large group, processed their results, produced a report that is, I think this is the report that he produced about, as it were, users' desires for what we might do in GHC. And then he discussed that again with us, and we did quite a lot. One of the top thing was to be more clear about how GHC as a project is managed, because it is now quite a large open source project with quite a lot of people who are, both their time and their emotional energy and sometimes their companies are deeply connected to the decisions that they're made. So we owe it to be a bit more transparent. So now there is a brand new GHC headquarters homepage. This isn't primarily technical, it's primarily organizational, right? What are we doing and how do we organize ourselves? And so here's the URL. You can go and have a look. It has pointers to finding out, what is going on with GHC and also how to contribute. So in particular, identifies much more clearly than before the GHC team, right, which is the bunch of people who actively contribute to GHC who have commit rights, right? So we now list them explicitly with their areas of expertise. It's a anybody can join the team simply by saying, I would like to join the GHC team, and then you get a standard invitation to come to the weekly meetings. The commitment you have to make is that you're then up for saying, oh, could you review this merge request for somebody else which is in your area, right? So it comes with some power and some responsibility, but the idea is that anybody can sign up. It's not a kind of closed shop. So have a look at this. The second thing the foundation did during the year, which I think was in GHC land, this isn't a foundation summary, this is just the GHC intersection, was to run the GHC Contributors Workshop, where many of you were at. So do go to this thing that looks like an invitation to the workshop, but if you scroll down, you'll find the program. And in the program, you'll find videos and slides for all the talks. So this is kind of like incredible. If you're interested in getting arms deep in code for GHC, this is a fantastic resource. It contains talks by the people, so Loiter and Cheng and so forth, talk in detail about the WASM backend and the JavaScript backend. You can get a lot of technical information here. So do take a look. But that was just organizing this at Zurich Hack was a pretty significant organizational effort. We're really grateful to the foundation for doing that because we didn't. And the third thing I wanted to point to was a long conversation which at times has been tricky in the past, but which has settled down in a really good way principally between the Core Libraries Committee and the folk involved, particularly in GHC, because there was this question about, originally the base library was kind of in GHC land. Really, it was just what GHC exposed. That's why it was called base. But now the Core Library Committee is in charge of it, and there was a bit of tension about, if GHC guys just sort of add something to it, or if the GHC Steering Committee, to make some enhancement to the language, adds something to the base library. Now the Core Libraries Committee feels a bit undermined, and that's not good, right? So we had miscommunication because of that. So we've sorted all that out now. It's got this nice structure, which I'm going to share with you because I think it's helpful to have in everybody's head. So here it is. The base library, right, is curated by the Core Libraries Committee. And when I say curated, I mean they're in charge of the API. Exactly what is exported from exactly what modules with exactly what types and their performance characteristics, right? So can't run out and arbitrarily change performance characteristics. So any changes to that API, we need to submit a Core Libraries proposal for. However, underneath that is a bunch. These three libraries packages are part of GHC's internal implementation. We previously had something called GHC Bignum and GHC Prim. GHC-internal is a new one, right? And it can contain whatever code seems good to the GHC implementers. You should think of it as being, that's the cogs and the wheels inside the machine, right? This is the surface. But if this guy, base, re-exports something like, I don't know, lists, which are actually defined down here, then it's no good us saying, well, we decided to change lists down here, and oh, and by the way, you just re-exported it. Not our problem. No, if it changes this API, we have to negotiate. So there's a transitivity involved, right? And then furthermore, the GHC steering committee may do things like snapshots, stack snapshots, or I don't know, tuple naming things, and we don't want to uncritically add those to base, because then they're part of this very strong stability goal that the Core Libraries Committee is going to maintain. So the GHC experimental package is meant to be under the curation of the GHC steering committee, and they're going to add things to there, and you're welcome to use them, right? And but they don't come with the same stability guarantees as the base library. So I put major goal stability here, goal here, and not a goal here. Does that make sense? Right? And these libraries here, you are welcome to import, but it's at your own risk, right? We will make no attempt to, we will not apologize to you if we break your library because you imported something from GHC internal. If there's something from GHC internal that you want to use that's important to you, then you should appeal. You should either get it in experimental or in base, at least, to, because that will then tell us that's something you care about, right? That we should be careful about its stability. But there's an awful lot in here that you don't care about, and we don't have a way to distinguish that. Does that make sense? So I think this is very helpful. It's all set out in this proposal, which is a Haskell Foundation proposal. And I will just remark, you can look up Conway's rule, right, that which is that the technical structure of software projects evolves to reflect the organizational structure of the groups that are building them. And there's a good reason for that. It's kind of tongue-in-cheek, but there's a good reason for that, which is that it helps with communication. Each group knows what it is doing and doesn't trip over the other. Does that make sense? So I regard this as quite a big victory, in that an area that was previously, there was no hostility, but there was tension. I think the tension has been greatly ameliorated by doing this. And the foundation played a big role in making this happen. Okay. A quick roundup of GHC proposals. Yes, Christian.
So things that are in experimental but then become stable and move to base, will they stay in experimental forever, or will they? On which package do I need to depend?
So initially you'll depend on experimental, right? And then you may say to the Core Libraries Committee, guys, this is really useful to me. I use it every day. It's been there in GHC for several years. It should really be stable. And they say, fine, Christian, yeah, we'll put it in base, right? And then we might use those deprecated exports to suggest that you don't import it from experimental anymore. You import it from base, right? And then several years after that, we might, GHC is turning into this sort of decades-long storyline of deprecations and gradual shift. Because we don't want to break your code gratuitously, right? Or maybe you decide to leave it in experimental forever. I don't know. That would be a case-by-case choice. Does that make sense? Yeah. Anyone else? Is this keeping this separate in your head? I think is quite important to understanding what to do. Yeah.
So the proposal is accepted, as I understand it. Is there a roadmap for when we can actually expect to see these new things on the bottom of the slide?
Yeah. So there is 9.10, right? Yeah. So 9.10 will have this, right, possibly empty, right? Because after all the code is here anyway. The idea is we will probably, in order to implement stuff in here that we want to stuff in here that needs internal stuff, we may need to move code out of current base into here, leaving shims behind, right? And there may be some libraries, some functions in base that are manifestly internal and were never intended to be for public consumption, and that the Core Libraries Committee may or may not agree to remove them from base and have them exclusively here. But that's a future conversation. Does that make sense? But these both will exist in 9.10. So as sort of placeholders to be filled out. Yeah. Okay. Quick roundup of GHC proposals. I mentioned them quite a lot in the headings for slides. So thanks to Joachim for getting these numbers. So we're up to 394 active, genuine pull requests. If you look on the website, you'll see 600 and something, but the others are somehow not proper proposals. So other PRs that weren't proposals, fine. So we've actually had 394 proposals since it began, right? 43 new ones this year. The number under discussion, meaning that they haven't been closed down. This is before submitting to the committee. They're not under committee's purview. They're simply under community discussion. The author hasn't yet submitted them. 66 of those. That's a few more than was in the case last year. Under review, the committee has got in its inbox 9 that's got to decide about, which is a little bit more than we had at this moment last year. That tends to vary over time. The total number of accepted proposals, 124. So we accepted 18 new ones in the last 12 months and rejected 2, and 20 proposals got implemented this year. That's pretty good. Right? Remember, accepting a proposal is not a guarantee by anybody that they'll be implemented. Somebody has to step up to do that. So these are the ones that I won't read them out. These are the ones that have got accepted this year. Ryan.
One thing I wasn't sure on that slide, some of the proposals that were submitted were amendments to previous proposals. Are those included under the accepted tab, or are these a separate category? Okay.
Yes. So some of those 18 are simply amendments to existing ones. Just putting up here the list of accepted ones. I shan't read them out. Here's some more. Okay, I think it's painstaking, sometimes frustrating, but I think it's basically a healthy process, this. Okay, here are the people you should applaud for their hard work. This actually is quite hard work doing this. I'm really grateful to all of the people who serve and the people who served in the past on this group, because it's yeah. Well, oh, closer to the mic. Sorry. Yes, thank you. Let me say that louder. I'm really grateful to the people who do this work. Thank you so much. Yeah, we can applaud them. Thank you. Which take me through. Let me just go back to the GHC team, because I want to Ben to just fill in a little bit about this, about the sort of the CI process and the number of tickets we got. This is so when I showed you that GHC HQ thing and said, here's the GHC team, we and anybody can become part of it. We wrote down a list of all the people we thought were active contributors at the time, and wrote to them all to say, do you want to be a member of the GHC team? With the powers and the responsibilities that has. And these were the people who are currently signed up. So big thank you to all of them. So GHC is quite a big project. These are the people who actively contribute to GHC on not a daily basis, but actually you'll be able to see in the next few slides how much they do in effect.
Yeah, I'll make this quick. But yes, thank you, Simon. I think on the whole, GHC is quite a healthy project. So here we see, looking at the number of contributors, how many have made N commits per year over the last year, or for each of the years, we're going back to 2009 or so, last 15 years or so, and we see that there's a nice upward trend here. And this 10 or more commits this year is roughly that list that we saw on the previous slide, right? We have around 30 people who are quite active, and not only in commit, actually writing code, but also reviewing and offering feedback, helping our contributors. So I think this is quite a healthy story. But this, on the other hand, is where we need help, right? So here we have, we see that this is not a good trajectory, especially given this trajectory here. This is much steeper than this, you'll note. So if you can do anything, it's open GitLab, go gitlab.haskell.org/GHC tickets, choose one and fix it. We would all be very, very appreciative. Yes, Lexi.
On the contrary, a large number of open tickets is a sign of health. People care enough about the project to file bugs.
That is quite right, but ideally they would, we'd also like to close some at some point, though, as well. That's sort of where we need your help. Let's see. Yes, so as you know, HF has been really helpful in offering to fund Brian Richter, who is now our DevOps, our DevOps engineer. He's been invaluable in helping support GHC development, as well as other projects in the ecosystem. And this is really important, I think. We need having somebody who really has the bandwidth and focus to be able to evaluate our infrastructure, not just within GHC, but also more broadly across the ecosystem, and be able to help out honing that infrastructure where needed. So this year he's been focusing largely on characterizing the fragile tests within GHC on the GHC side, and looked a bit at notarization of our Mac OS artifacts, and I think we now have a plan for doing that. I'm not sure it's going to happen for 9.8, but we shall see. and generally trying to make our infrastructure more maintainable. And so for a long time we sort of muddled through because it was me and a few other people. Now we have Brian, and Brian has been working to further cast even a wider net in making our infrastructure sort of a more community asset and less of something that is just GHC responsible for overseeing. Likewise, we've made really great strides in, thanks to Brian's help, in reducing spurious, the reliability of our infrastructure. So, over the past year or so, we've had roughly a 50% reduction in the number of spurious job failures, which I think is really, we've gone from 85% or so to greater than 90% passing rate, which is really, helped. It makes it much nicer project to work on when you don't have to randomly restart 3 jobs that spuriously failed when you submit a merge request. We have, of course, been continuing, head.hackage. We last year we reported that we were advocating for a proposal, ghc.x.hackage, which, based upon our head.hackage infrastructure, the fallout of that proposal was, well, there may not be enough interest necessarily for end user use, but head.hackage continues to be an invaluable resource for testing GHC and ensuring that we catch real world issues from on hackage code as they are introduced in the tree. And I think Ryan is somebody who really deserves to be noted here as being somebody who's really looking carefully at head.hackage and making sure it remains building and catching bugs when they occur. And this has, in fact, really caught real bugs. And I think our releases are are in much better shape by the time we start the pre-release cycle because of head.hackage. Right. So let's see. We've as well been introducing support for nightlies for end users to be able to easily get nightly builds of GHC via GHC Up. We hope that this is a useful resource for our users, especially those who are wanting to use sort of pre-release features. And head.hackage, of course, is a great resource for them as well. Likewise, and finally, Hadrian, we can finally, at long last, we put the last nail in the coffin of the make build system. It was dropped in the tree as of 9.6 after a long road. I think we started working on Hadrian. Simon told me about Hadrian when I started working on GHC in 2016, I think, and now here we are in 2023, and we just barely removed the make build system. So it was a very long ordeal, but I think the result is actually quite good, and we managed to work with our packagers to address their needs. We're still sort of working on continually improving the build system, and certainly we're now starting to reap dividends of all of this work, especially with the cross-compilation work that we're now undertaking. So, in general, this is a community project, and there are countless ways in which you can be involved. We certainly have no shortage of tickets to look at, but as well, there's so many opportunities within the ecosystem, from the GHC Errors project to various work across the ecosystem enabling JavaScript and WebASM support, to looking at compiler performance features. See the newcomer label on the BitTicket tracker for ways in which you can help. And thank you for listening. I think that was yes.
To that, it's kind of tempting to see GHC's been it's a 33-year-old project now, and it's awfully tempting to see it as something that will happen anyway, right? Just sort of out there, and I can use it. But this is the Haskell implementers meeting. Quite a lot of you have spoken today because you're active contributors. Some of you not, but I would really love you to become active contributors, because we're only going to succeed if GHC is our project and not, Ben's project or my project or some anonymous team. Really, really significant that we think of it as being something that we are doing together. It's quite, 33 years is pretty old. That's slightly older than my eldest son, who is now an active contributor to to HLS. So you've got to breed them. But that's that it's quite. it's quite rewarding to contribute to something that's as long-lasting and as I would like to think, you know, as intellectually and organisationally important as GHC is. So please do get involved. And if you find yourself bouncing off in some way, you try to get stuck in and things haven't quite worked out, or you felt someone was unfriendly to you, or just that you couldn't find a way in, then talk to Ben or talk to me or talk to somebody. Don't just sort of go away and cry. All right, because particularly in a big geographically distributed system, it's easy to accidentally miscommunicate. So go the extra mile and write to Ben or write to me, or talk to us later during ICFP. Thank you so much. Great. Yep.
Hello, yes. This is a question for Ben. So Make has been finally deprecated. Are there plans to remove the vestigial parts of it from the G? Oh, I must fetch upstream. Excuse me. Thanks.
Yeah. Good riddance, I would say.
I actually have a question for the room. So I'm sort of the not so secret person behind these error message codes for years. Even sort of before the HF happened, we started to put the error message codes into GHC, and then I encouraged the HF to sort of take this on. And there's been a lot going on. Many other people contributed. I didn't do any real hard work. I just sort of stood behind the scenes and cheered on. I'm curious, do people use these error message codes? I mean, I see other people contributing to this and other projects starting to use it, but I don't have a good sense. Was this a good idea? Like, what? Can I have a raise of hand of people who have actually looked at that errors.haskell.org to get information? Okay, that's pretty cool. So, I mean, can I get like nod? Like, was it helpful? We have yes. Okay, good. I mean, or you have students who maybe there's a bad sample set because I think a lot of people here, and I recognize that, but maybe you have students or other colleagues. Anyway, even a little feedback was helpful there. Thank you.
Maybe you have time for like one or two more questions if anybody has them.
So this is more me being out of the loop. What's the status of the FAT interface files? Is it in 9.10? Could we have FAT interface files for base as a separate download? How difficult would that be?
I believe there is actually a ticket about that. Yeah. So this prefer bytecode work actually relies on. I believe so currently we do actually have some core interface files. If you opt in, we don't ship binary distributions with this with such core in interface files, and there's a reason for that, and that's size. This is yes, we could optionally we could ship this as a separate sort of artifact that one could download. I think there's a real question here is it's a distribution question as how do you actually ensure that how does the user actually download this, install it, and ensure that GHC can that they're compatible with the interface files that would have been in the binary distribution that the user originally downloaded. Either that or we need to produce two binary distributions for every platform that we offer, which is not really a great option. So I think there's some design work here, but I think a lot of the similar questions need to be answered in the cross compilation work. So I'm hopeful that because for instance, when the user wants to start, they download their binary distribution, you have a runtime retargetable compiler, and all of a sudden they say, oh, I need to compile for AR64 now. Well, you need to download a whole bunch of things for the runtime system text, the core libraries for AR64 as well. So this sort of adding things on to an existing binary distribution is, I think, something we're probably going to have to address one way or the other. And this is just another example of this. Debug information is another example, and IPE information. There are many things that would sort of be helped, I think, with such a mechanism. But yeah, it's sort of a cross-project piece of work, since this is ultimately probably something that is pretty squarely in the GHC up category of area of responsibility. So yeah, there's some design work there, I think. Yes. Oh, sorry.
Unfortunately, we are out of time. Sorry about that. Oh, the question is, where can we see where the lightning talks are? So if you go to the program on the HIW track on the ICFP website, we have a list of them. I've noted that you submit a lightning talk. I haven't had a chance to add yours yet, but I promise you I will get around to doing that. So yeah, sorry about that. I have to manually add these, so I haven't had a chance to get to my laptop and get the forums modified appropriately, but that is in the works, I promise. All right, well, that is all the time we have, so let's give a round of thanks for our speakers, Simon and Ben. All right, we're now going to have a 30-minute social break. We'll be back at 11 o'clock.
Go to settings, the Zoom settings. There you go. I'm trying to. Oh,
Share sound. There you go. Okay, I'm sharing sound.
it looks like there's something.
I'm getting an answer there. Okay. Perhaps we should just resume, go away with the session since I don't want to spend too much longer on this. We did, yes. Sorry, we were looking at something unrelated to that.
And also avoid the speakers.
Where?
This should not be hide in the pockets.
Hi. Okay, outside.
Yeah, just
Okay.
click.
It works. Okay. So I need my screen back on the projector because that's not mine.
Oh, yeah.
Oh, maybe we
Oh. I'll try both permutations. Okay.
I'm gonna.
Hello? Hello? Sorry, we are still having technical issues.
Oh.
So I could try to start anyway without slides, but as you wish.
We still have some time. We're going to have a lightning talk this session, but the speaker didn't show up, so we'll have some extra time to make up as a
Something on your side, you need to refresh something?
No, I still don't have this projector, so.
Will you need to give a demo, or could you?
No, just the slides.
Could you have the slides on his machine instead?
Yeah.
Oh yeah,
Absolutely.
I guess if it's that problem then.
You might know Liquid Haskell already is this static verification tool to which you read one program and a specification, and it verifies that the program behaves as specified. So in this talk, I'm going to try to convince you of two statements. The first statement is that Liquid Haskell can make Haskell better, and that is by way of offering support to avoid mistakes when writing or modifying programs. And the second statement is that in order to succeed at this, we are going to need the help of the GHC developers. So Liquid Haskell is integrated with GHC to some degree, and whenever there are changes in GHC, Liquid Haskell needs to be updated, and here we need the help of the GHC developers to anticipate or to identify problems that might come in the integration. So in this talk, we are going to see at how Liquid Haskell depends on the GHC API, and I'm going to discuss a few ideas of how the teams could collaborate in doing the updates quicker. So to see how Liquid Haskell can make Haskell better, we have to look at what Liquid Haskell can do. There's a range of things that it can do, from most modest to most ambitious. So let's start with the modest. Liquid Haskell can verify that invocations of partial functions don't fail at runtime. If we have to get the first element of a list, well, Liquid Haskell can ensure that the list is non-empty.
And if we need to get an element from a container, well, Liquid Haskell can ensure that the position in the container where the element is supposed to be actually exists. Another use case is safe pointer arithmetic. So Liquid Haskell can ensure that the pointers that are used in our programs are valid. And here valid means that the memory that these pointers refers to has been allocated, and therefore is safe to read and write without producing undefined behavior. And yet another use case is verifying data invariance of data structures. So Liquid Haskell can ensure that all the data structures that are used in a program are actually valid. And here valid means something different for each kind of data structure. So if you have a binary search tree, or you have a binary heap, or a custom data structure, then each data structure has a different notion of validity. And Liquid Haskell is flexible enough to accommodate all of these notions and use the appropriate one each time. So these use cases are described in this paper, which also has a couple of case studies, one for verifying an implementation of red-black trees, and another one for verifying data structures in the XMonad tiling window manager. So now going to a more ambitious use case, Liquid Haskell can be used to manage optimizations. Suppose we have a simple function that has become a bottleneck in a project. Then over time, developers come and implement optimizations that preserve the behavior of the function, we hope, but make it run faster. Now, optimizations have the unfortunate effect to make the code harder to understand. So when enough time passes, the function might become so complicated that nobody dares touching the code again, because it just might break and nobody has a precise understanding of how the function should be modified. And this is why earlier this year, Conal Elliott was arguing that optimization is self-defeating without proof, meaning that if we had a proof that the implementation is equivalent to the original function, then we could optimize the implementation by also updating the proof and getting a guarantee that the behavior hasn't been changed. Now, Liquid Haskell can help deriving this optimized implementation and check every of the steps of the derivation. And I also gave a talk last year where I demonstrate the point with a complicated function in the base library. So another use case is using Liquid Haskell as a stronger type checker. There are aspects of the programs that are difficult to express with the Haskell type system alone, and sometimes Liquid Haskell specifications can make this easier. This is a post discussing how to use Liquid Haskell to describe the type of well-typed lambda terms. And there's another use case in the works that is trying to use Liquid Haskell to give types to expressions or to values that are in a foreign language. So we have a few more use cases. I'm going to go over those just to give you a broad idea of what Liquid Haskell can be used to. It has been used also to prove that the memory and the CPU that some functions use is bounded. It has been used to verify that web applications don't leak information to unauthorized users. It has been used to prove properties of distributed computations, and you get some guarantees about the global behavior of a distributed system. And lastly, there are some use cases that haven't been explored yet, but which are, it's plausible that they could be supported in some future. So why is all this important? Why would we be interested in making Liquid Haskell succeed? And the thing is that Liquid Haskell is not a tool designed for a specific use case. It's a tool that can inspire solutions in a wide range of domains. And it gives the opportunity to tap into the creativity of the Haskell community, to explore all those domains. So this would enlarge the range of things in which Haskell can grow and be applied. Another motivation to to try to have Liquid Haskell succeed is that it offers different trade-offs than traditional approaches to dependent types. And if we have these different trade-offs, then this is likely going to lead to different innovations when compared to the current trends. And one last motivation is that there are industrial applications that are within range or within reach. And so we could develop Liquid Haskell while addressing these industry needs and get in return some support for maintenance. And so this is why I think it's worth giving Liquid Haskell a shot. Now perhaps this is a good time to answer questions if anyone has any thoughts. Yes.
Dumb question.
Yes.
Can you use Liquid Haskell to prove that you can elide array bounds checks?
Yes, that's in the category of partial or verifying partial functions, right? That they don't fail at runtime. So with
Has anyone done it? Do you know whether it works well?
yes, yes. There is a talk by Gabriela Gonzalez from 4 or 5 years ago in Haskell Exchange, where she goes through a concrete use case of using Liquid Haskell to speed up parsing library for UDP packets. And yeah, that's exactly a case of removing runtime checks and relying just on Liquid Haskell to check things statically. All right, any more questions?
Are you coming to an end, or have you got more to say?
No, I have more to say.
If you have more to say, fine, I'll wait.
Okay. So on to the next question. Why do we need the help of GHC developers? So I'm going. We need to look at how Liquid Haskell uses the GHC API to answer that. So at the moment, the specifications of Liquid Haskell live inside special comments in GHC. So one first thing we need to use the GHC API for is to extract the comment from the source code. And then when we are going to analyze a module, we need to understand what the imported functions in that module or how they are supposed to behave. And this requires learning their specifications that are stored in the interface files of the imported modules. So we need to use the GHC API to load these interface files and get the comments and the specifications from there. And Liquid Haskell is going to analyze GHC core. So we need to deshure Haskell to GHC core in order to run our analysis. And then when we have GHC core, we run the analysis, we produce a list of proof obligations. And if all these proof obligations are going to be given to a theorem prover, if the theorem prover is satisfied that, or can prove all of them, the module is set to pass verification. But if some of the proof obligations cannot be proved, then we need to report some errors to the user. And we are going to use exactly the same interfaces that GHC uses to report compilation errors. And one last use of the GHC API is to store the specifications of our module in the interface file. So modules that import our module can learn what the specifications our functions have. And it's part of maintaining Liquid Haskell is maintaining these uses of the GHC API. And there's a problem, which is that Liquid Haskell is like near 3 versions behind GHC, the last release of GHC. And whenever there are changes in GHC, usually we have to make changes to Liquid Haskell. And the last time we did this was for version 9.2 of the compiler, and it took around 10 days. So it's quite some effort to update Liquid Haskell now to the latest version of the compiler, and we would like to make Liquid Haskell quicker to update. So, but there's a challenge, which is that the information necessary to do the updates of Liquid Haskell is distributed between the Liquid Haskell developers and the GHC developers, and we would need to get that information together into the same heads. So, from the GHC developers' perspective, if a change in GHC breaks Liquid Haskell, it's going to be a challenge to figure out how the old behavior was used in Liquid Haskell, so it can be recovered or replaced. And Liquid Haskell is quite a piece of software. The part that interacts directly with the GHC API is 30,000 lines of code. But if the change in GHC is subtle enough, a debugging session is probably going to send the developer into all of the components in Liquid Haskell. So this is not a very bright perspective, I think, for GHC developers.
30,000 lines of code directly interact with the GHC API?
Yeah.
Ah.
Yeah, that's like the bulk of the code that does the analysis of GHC core, and that's all the uses that I listed just now. Okay, so so from the perspective of the Liquid Haskell developer, instead, it knows exactly how the old behavior of the GHC API was needed, and it also could evaluate quickly if a new interface could be used to replace that behavior. But what it doesn't know is exactly how the GHC API has changed, and it doesn't know exactly what concrete interfaces are available to replace or to recover the old behavior. And this is where we need help from GHC developers, and where we would need we need to solve a communication problem. This is not so much a technical problem as a communication problem between the teams. So an effort to stabilize the GHC API would help, but I think we can do we can take smaller steps, like to address the problem. For instance, suppose that we collected a list of all the functions from the GHC API that Liquid Haskell needs. Now, whenever this, and when we collect the list, we could also collect the types that, or the type signatures that we expect of these functions. And whenever there's a change in the compiler, we could expect to automatically know that something has been broken. And this could, and then either team could start a conversation about how to resolve it. Moreover, this list would inform API stabilization efforts. So people doesn't know to browse all of Liquid Haskell to learn how it depends on the GHC API. Another step in this direction is to write tests for specific assumptions about how the functions behave. Liquid Haskell has been sensitive, for instance, to how case expressions are desugared. So if we write a small test that says, well, this is how Liquid Haskell is expecting the sugaring of case expressions to happen, then when that assumption changes, we can discover it quickly by running the test and seeing that they fail. Also, for a GHC developer, it's easier to understand how Liquid Haskell depends on the sugaring by looking at this test instead of having to figure out how the Liquid Haskell tests have failed.
So it sounds like you're really depending on more than just the list of GHC functions and types, but also something about the semantics of the compiler itself, how it translates Haskell into core, I guess, right?
Yeah.
That's a bit harder than, I guess, the just API guarantees.
Right.
Yeah.
Okay. Yeah, but it's going to save, the point is to save debugging effort. So we don't need to debug the Liquid Haskell test whenever these assumptions change. So I think Simon has a question back there.
So I think this would be really helpful, actually, because we've had, for a long time we've aspired to have a project to define the GHC API, and here's a concrete use case. And we don't have to define all of it. Just defining the part that you use would already be a step forward. But it's more than just a routine question of listing all the functions that you happen to call. Because I'm sure that what you've done is you've just reached out and grabbed the function that seemed most plausible that day, right? And because that happened to be available. I suspect there might be a more active process about saying what function would we like to have and its semantics. So, we happen to have reached out and got that one because it's available. What would be perfect would be to have this, right, which would replace these 3 others. So I think it would be more than a routine matter, even on your side, to define what is the API that you want.
Yeah.
But it would be a very valuable exercise. It'd be really helpful to us.
Yeah. I think before engaging in this conversation, I'm going to just go on with the next slides because I think, yes, we need to complement these ideas still with some more dialogue about how to use the GHC API. And all right, so this is the idea about the assumption test. And another idea in this direction is to run this test periodically somewhere, but then we need to agree how to respond to failures in these tests. And one idea here that I think could work is if the GHC developers maintain a log of where each entry is going to explain where for this test failure in assumption test. This is what the Liquid Haskell developers could do to recover the old behavior, if that makes sense, if recovering the old behavior makes sense. Or rather, the Liquid Haskell developers should really be using this other interface to accomplish this task. And note that this idea generalizes to any client of the GHC API. It's not just about Liquid Haskell. And also having test suites with assumption tests is like we will have focusing what's the documentation effort that needs to be done in order to stabilize the API, because if nobody's test is being broken with a change, there's less of a motivation to document it. On the other hand, if we know that some expectation has been broken, then perhaps it's fine to leave it without further comments. Okay, so I would like to finish with a small perspective. Oh, we have a question. Please.
Just propose. Uh-oh, I don't know.
I think I can repeat the question anyway.
Okay, yeah.
Okay. Do you think it's possible Liquid Haskell CI to be integrated into GSC CI? So if someone breaks the behavior of GSC, or not breaks but change the behavior in GSC, it will fail Liquid Haskell CI directly, and this will report Liquid Haskell team directly. So if both CIs are integrated, I mean, better Liquid Haskell CI into as a steps into GSC CI. So all the merge requests in GSC will be tested via Liquid Haskell CI, and this will be another test for GSC. I don't know if this is feasible, but maybe you both could talk about it.
Yeah, I think that maybe adding all of the tests of Liquid Haskell into the GHC CI is not a good idea, because you need so much knowledge about Liquid Haskell to understand why such a test is failing. That I think we wouldn't want to stop Liquid Haskell developers from making, or we wouldn't want to stop GHC developers from making progress because CI is red, right? So it's more like, but I think we can provide this assumption test that should be smaller and only mess with the GHC API. So there should be no specific about Liquid Haskell there. And when these tests break, GHC developers shouldn't be forced to fix them, but they should just comment on how they think they should be fixed.
It could be optional test.
Yeah.
Not to break the GSC CI, but it will show that something is broken by the changes, by concrete changes in GSC.
Right. Yeah. So it's some arrangement like that.
Small steps, because not on the later when there are a lot of changes in GSCI, and you to try to fix liquid Haskell over the whole chunk of changes, and it could be fix it on smaller steps, which will be much faster to fix in early stages. Shift left approach.
Yeah.
There's precedent for including such packages in head.hackage, for what it's worth.
Mm-hmm.
And there's another question.
Yeah. Is this on? Okay. Anyway, just following on to that, can you hear me? Yes?
Yep.
Okay, great. I'm hesitant to add more to the GHC CI because we don't even have enough CI capacity for like the JavaScript backend's performance build, so don't expect performance real just yet. But also, couldn't you, the Liquid Haskell project, pull down GHC nightly builds and then test their CI with the GHC nightly?
I suppose so, yeah. But I mean, let me make this clear. It's not difficult to come up with a scheme to run the tests and to monitor when they fail. So I think the real difficulty is how do we fix Liquid Haskell then quickly, without doing too much debugging and too much figuring out of what has changed in GHC. So I think for the sake of time, I better finish my slides, and then if there are more questions, then we answer them in the hall or here if we have time. All right, so to finish, a brief perspective of the evolution of Liquid Haskell. It started as a verification tool for OCaml, actually. Then it became a verification tool for Haskell, and some years ago it became a GHC plugin. And the experience with the GHC plugin, I think it has been fantastic when compared to the experience before, because the GHC plugin allows to share specifications across packages, and it also delegates to GHC the problem of deciding in which order to verify the modules, because you need your dependencies verified before you verify the module. So it has been great. Also, the GHC plugin is very handy to fix Liquid Haskell, rebuild it, redeploy it, and this works in absolutely any Haskell project. Right? If Liquid Haskell were further integrated with GHC, then we will have to fix the compiler, rebuild it, redeploy it, and I think this is more of a challenge in general. Or perhaps sometime in the future, we still could keep the advantages of the GHC plugin, but still get Liquid Haskell closer to a language extension, perhaps deploy one day together with a compiler, so it's easier to try and to adopt. But I think the advantages today of the GHC plugin are a serious thing. Whatever the path we decide to go further, I think the communication problem is going to remain and needs to be solved. And with this, now it's your turn to lecture me on how you think that our teams should collaborate. Thank you.
So from my perspective, I think there definitely are a few things that we can work on together here, and I think a lot of this comes down to, as you said, starting with a concrete list of things. This is interfaces and assumptions, and starting to work on making those into something that the GHC, adding essentially. Historically, the GHC developers have treated the GHC module itself as the GHC API. Anything beyond that particular module named GHC in the GHC library is sort of internal to GHC and not to be yes, okay, sorry, and not to be treated as stable. But of course, you can do very little using only the things in the GHC library, the GHC module, that is, and that's something that we've long needed to improve. So having a list of things that we can start to sort of consider, okay, maybe these exact interfaces aren't the things we want to add into the GHC library, since they may be unstable or they may not have quite the right semantics that you want, but at least that gives a starting point for discussion. I think the HF as well is, David Christensen is working on finding people to resource a effort to actually stabilize some subset of the GHC API and work with projects exactly like Liquid Haskell to make this an API that's usable for users. So that it would be a really, but in the short term, I think just we should start by opening a GHC ticket and starting the communication there, and try to hone a concrete list.
Looking forward to that.
One last question.
Oh, I just wanted to mention, with respect to the Haskell Foundation project, I mean, this is something that I've, obviously David is now moving on to other things, but this is something that just in like the past few weeks, we've been talking about very explicitly. And in, it'd be great if it were a little farther along for this particular event, but we definitely want to kind of start by just putting together a sort of, I don't know, committee has such a bureaucratic connotation to it, but just a group of people, a group of people who are actively trying to do things like this. And I think it's challenging because, for some people who want to get information out of GHC, it's like, things like Google, right? The interface can be very thin, whereas for things like template Haskell or liquid Haskell, it has to be a lot. You were saying you depend on like how case is desugared.
Yeah.
And so for stuff like that, I do think it would be really, really helpful, as Simon kind of mentioned earlier, to think about like what in an ideal world would this look like? Because I think in the past our approach to trying to create a GHC API has just been to say, well, we've got this stuff sitting around in GHC and we can just expose it. But this doesn't really work very well because then things break and you depend on implementation details. So it would be very nice to have some, greenfield API that can serve that sort of use case.
Was that the question?
Well, I think the question is asked to the audience.
Yeah.
Well, I think in the interest of time, I have to cut that short. Thank you again, Facundo. Our next speaker is Dylan. Is Dylan in the room? Oh, please go back there.
Yeah, I'm giving you back the mic right now.
Oh, wow. Oh, yeah, sorry.
There's one right here.
Oh, wait. What? Oh,
there's an actual.
So much, even better. There's so much going on.
Yeah, hopefully that doesn't catch fire.
Oh boy. Yeah, I do. Oh boy. I really want to even. Oh boy. Oh.
Yeah, it's a little crispy. But that's good.
We need a few more seconds to get set up, but our next speaker is Dylan Fins on error message annotation and plugins for Haskell, whenever you are ready.
One sec, let me just get the HDMI output going.
The roving microphone is gone.
right, so Dylan Things on error message annotation plugins for Haskell.
Right. So I've got quite a few slides, so I might start speaking rather quickly. If I start doing that, please feel free to slow me down. Just raise your hand or something like this. Right. So error message annotation plugins for Haskell. So as a sort of brief first overview, what are we going to be talking about? What is this? I'm going to be staring down at the ground the whole time. Essentially, I'll be outlining a new plugin interface that I'd like to propose. Its main task is that it should allow you to improve type error messages without actually having to hack directly on GHC. There's no formal proposal yet, and the reason for that is really that the changes are actually quite minor, but I do feel like there's quite a lot of input that you want to take from a bunch of people before you want to make a proposal about this, because it's going to evolve quite a lot long before you actually have anything concrete on a piece of paper. So basically what that means is this is still very early stages. So if you hear something that you're quite interested in, or if you hear something and think, by God, that guy's an idiot and he knows absolutely nothing, this is perfectly, please join on in and you can make modifications. Right. So, as a brief overview of what we're going to be going, I'll be going over first 5 sort of issues and goals, which are sort of noticed that this is sort of looking to tackle. Then we'll actually be detailing the, prior work will go first, then the error message plugin approach will be sort of detailed, then we'll go into implementation, time willing, and then we can show a couple of examples of plugins which have been built on top of this sort of new plugin interface. And then finally, we go into what's next. So the basic idea is that type error messages are hard, right? Now, I don't want to sound like a wimp when I'm saying that, but at the end of the day, it is actually quite an interesting problem, right? You've got people who are producing type error messages and people who are consuming them, and they've all got sort of slightly different goals or interests, which aren't necessarily at cross purposes, but sometimes might be pulling in interesting directions. So essentially the end result is that you need to sort of think about what are these sorts of unique desires of some of these different groups to see what you might be able to design. So first issue is one that we're all familiar with. Many beginners find Haskell types intimidating or difficult, right? I mean, as much as we all like to tell ourselves we're good at Haskell and things like that, everyone in this room at some point had to learn that a string and an int are different things, right? And for some of us, it came on day one. Some of us, like me, spent 5 years writing JavaScript and had to have it beaten into us gradually. But so the sort of basic goal then that this issue creates is you want to give them better, more well-explained messages, right? Simple goal. Next, you have an issue, which is that it's going to be difficult to gather consensus on ideal error complexity. Some people are going to want, you've got a very large community of people who are consuming error messages. Some people are going to want, very, very fully detailed explanations of what is the error that they're encountering. An int is not a string, and a string is not an int. And other people are going to want something filled with jargon that they're used to, that they can quickly skim and really get the details that they want out of it. So really the goal that I took away from that is that you want something like an opt-in only model to avoid having to bring around the whole community on a single error improvement before you do it. Then you've got issues 3 and 4, which have to do mainly with library implementation, right? So when you have a library with very complex inner type machinery, we still have the problem that if then somebody uses that library, it's you have a surface DSL or something like this, in a way that doesn't type check, very frequently that inner type machinery is going to be revealed as the full hydra that it is. And this is type machinery which you probably haven't documented or probably haven't fully explained, and which really the person who's using the DSL shouldn't have to be interested in, because if they wanted to be interested in that, they wouldn't be using a DSL, right? So that's one issue. So you'd like probably to be able to hide some sort of complex inner type machinery when possible with custom errors. And then also, of course, complex inner type machinery is hard to diagnose, right? So you want to be able to provide as much information as possible for type error diagnosis. And then finally, this isn't really a goal, but or really an issue per se, but you know, GHC error generation is already pretty complex. So if we want to do something in this sort of sphere, probably don't, you know, go changing the entire system, you know, ripping things out and plugging things back in. Try to keep things relatively minimal when it comes to increasing complexity within GHC. So, right, so those are the sort of 5 goals and issues. You know, this is your goal summary map. These are the sorts of things that we have in mind, right? So, right, how do existing approaches sort of apply to this? If you want to tackle these sorts of goals and issues, what can you use in terms of existing approaches? Well, so you've got type error and unsatisfiable, which Simon really helpfully pointed out. The whole talk that I was listening to Simon, I was thinking, well, great, he's just preempting everything I'm saying. But right, alas. So, you know, type error and unsatisfiable, for those who are not too familiar, you know, you can have a show instance on A to B, and then say if somebody tries to show a function from A to B, they then introduce this type error, right? And then that's going to be essentially a special message that gets injected or you know, thrown out when somebody tries to show a function from A to B. Now this is quite nice. Of course, the proposal for unsatisfiable points out a lot of the interesting issues with type error, but roughly speaking, it fits quite nicely with the existing mental model that people have of Haskell, right? As in, like, they are aware of class constraints that are introduced and then dispatched with, right? So telling them, oh, this is a type error that is a class constraint, actually works kind of nicely. And of course, it's an example of custom error messages. Fantastic. So great, you've got some of the functionality that you want out of this. Now, the DAML-C compiler, and this is where we sort of first encountered this problem, was at Digital Asset, we have this compiler for a smart contract language, which is essentially a DSL built on top of Haskell, right? But the problem was our clients use this DSL built on top of Haskell, and then they do something wrong, and all of a sudden they get the full Hydra internally, right? And they don't want that. So we went in and modified the compiler pipeline error message output phase. It was really easy to implement. We added basically a module, and that was it, right? Now that's nice, you know, in the sense that you haven't made too many changes to GHC. So it fulfills that goal 5, but of course, you know, you did have to compile in your logic. So you're not really going to get this to first years who are learning Haskell for the first time. Because, yeah. Elm is another kind of interesting example of something that we can learn, that you can learn from, or that can give us some thoughts about the goals and issues. Elm has well-detailed errors, incredibly well-detailed errors, right? And then combines them nicely with source locations and details all the mismatches, but really detailed, right? As in, like, it tells you about the flow of the types through the pipeline and things like this, right? It really has this sort of flowery view of the world, and it's trying to bring that type level world down to the person who's ultimately just trying to build a user interface. So, and of course, what's nice is that they document their ideas on type error emission. So that's quite nice. It sort of fulfills goal 1. Then you've got the Haskell language server, which does a bunch of really useful stuff in that it pulls info out of errors, it pulls a bunch of information out of each individual stage in the compiler pipeline, and keeps them all around so that I can helpfully provide more and more information to the IDE. So this is useful, but also what's useful about the Haskell language server is it has a plugin interface, right? So you can write plugins for the Haskell IDE. So now you no longer need to get everybody's consensus before you try to improve LSP for Haskell, right? You can write a plugin, give it to your friends, and they tell you it's good. And at no point did you have to force everybody come along with you. So that's something to sort of take away. And then you've got, you know, another example is the Helium compiler. I don't know who's heard of the Helium compiler? Oh, okay, good, fantastic. Right, so, you know, built from the outset to have a core that can be extended a little bit more easily, provides a lot of extra information for more in-depth error analysis. Really just sort of is useful in the sense that they provide a lot of information, right? For diagnosing these really complicated type error messages. So what do you get out of these approaches? I mean, each of them give a bunch of useful takeaways, right? The Elm compiler changes to integrate well with existing messages, right? DAML-C, you want to isolate your changes. Type error says that, you want to trigger your custom error logic when you detect certain patterns, because that way it doesn't get too complicated. The Helium compiler, gets some information out there. And HLS tells you, okay, plugin model will help solve this consensus issue. So, great. So then we try to bake these sorts of ideas, and just 5 left. Okay, so we put them all together into the error message plugin approach. Oh boy, okay, well, turns out I talk a lot slower while I'm on the podium. Anyways, yeah, so for those of you who aren't familiar, GHC has a plugin interface where you essentially define a plugin module and then you can, inject it into the pipeline, right? So this will now change the type checking behavior of the pipeline, right? So our proposal then is to add a new handler, error message plugin. So this triggers when a message is emitted. So this is essentially your pipeline. Your type check is going to occasionally emit a TCRN message. That's sort of the error, right? I mean, there's a bunch of other structs, but let's keep it simple. So we propose instead, you can add an error message plugin which can intercept and rewrite these error messages, right? So why is this useful? Well, if you assess it according to the sort of goals, right, which each of those previous approaches were sort of getting at, you get some nice results. You can annotate or wholly replace error messages, so you can actually give users better, more well-explained messages. You can provide as much information as possible for type error diagnosis. You're running during the type checking phase. You have basically as much information as you're going to get. You don't really increase the compiler complexity too much. When we implemented this, it came out to about 100 lines, and most of it is boilerplate for anyone who's written a GHC plugin. And then for libraries, you can effectively hide complex inner type machinery. And then finally, all the plugins are opt-in, so you don't have to deal with a consensus issue. So, right, implementation, you know what? Anyone who's written a plugin, or there's plenty of blog posts out there telling you how to write a GHC plugin. So this is going to look pretty simple to most people. You have an initialization phase, and each error message plugin creates a rewriter. And so a rewriter takes a renamer message and then produces a rewrite. And this rewrite just gets attached to it inside of a struct. So it gets injected inside there, and what this means is that future plugins essentially can look at what was the error message before we rewrote it, before we annotated it. So once it's rewritten, we add this new variant, and by keeping the old message, all plugins can ignore the changes of previous plugins or use them to help inform them. Yes?
Just to be clear, so go back a slide.
Mm-hmm.
So that thing TCRN message, that's the existing algebraic data type for the message, is that right?
Yeah, yeah.
Okay. And so then you're gonna and your rewriter doesn't change that at all, you're saying. It just returns some extra information in this TCRN message plugin rewrite, is that right?
Yeah, it essentially injects a little bit of extra information. So we've also got TCRN message detailed info is sort of a similar pattern where you wrapping a TCRN message with additional state to help pretty print it differently, essentially, right? So we can jump to where we actually report the diagnostics. You can see here we actually, whenever we get a new rewrite, we just inject it alongside the original message inside of this struct. I mean, I'll make these slides available,
But ultimately, what effect does ultimately that have? That
Well,
it gets rendered somehow in the end?
Yeah, so in the end, the side effect is that when the pretty printer triggers, it will, depending on this rewrite, either attach a bunch of additional information and some additional hints, both can be null, or it can wholly change the original type checking rename message. So the pretty printer will, when it sees a rewritten plugin message, right, a rewritten TCRN message, will pick up this information to figure out how should it print it. So the kind of nice benefit of this, right, is now you have essentially an interface by which you can change the error messages that GHC produces, or you can just annotate them with additional information. But you have this sandbox now. So now if you want Elm errors, Elm-like errors, for example, you don't need to tell the GHC compiler team, oh, this is my merge request. These are all of the changes. I promise that I will maintain them. You can build it as a separate plugin. GHC doesn't need to interact with it at all. It just needs to provide this interface, essentially. Yeah. There's a few examples. A Haskell error index plugin. It attaches a blurb for the error code. So it just is a plugin which finds this error code and then injects in some additional information for the error code. So it pulls out the blurb from the website. You have the same for GHC has field struct errors. You can always detect things for no instance shape and just attach a little bit of information that says, this is what it actually means. The field Z is not defined on point 2D, and these are the structs in scope that might have such a field. Similarly for specific libraries, right? So now if you have a library with complex intertype machinery, I mean, Lens is sort of stretching that definition, but it still works. If you try to use a prism as a lens, right, the error that you get is incredibly instructive. It tells you that you don't have a monoid instance, right? So for this, it's actually quite nice because you can write a plugin which just says, am I seeing a lack of monoid instance? Is the origin from an identifier that was imported from the Lens library, right? And potentially with a little bit more information inside of constraints, you can, with potentially a little bit more information stored inside of constraints, you could even figure out that, oh, that monoid instance comes from the fact that we're trying to solve an applicative instance, which we're trying to solve because we're trying to get a choice pro functor, something like this, something that is classically Lens-like. So the result then is, well, oh, okay, so one slide got dropped, but point is here it injects a message which says, looks like, just like Clippy would, it comes up and says, looks like you're trying to use a prism as a lens. Would you like to change that, right? Would you like to use caret question mark instead of caret dot? So that's what you would see down there if I knew how to create PDFs. And then of course, you can also use this for shenanigans. A few days ago, I thought to myself, well, here's something fun you could do. You could emulate the good old days when errors were screamed, right? Like you've got this old quote, I don't know if anyone's familiar with it, real programmers don't write Pascal or write in Fortran. As this quote, a real programmer said things like do 10, I 110, and abend, and they actually talked in capital letters. Well, now you can get GHC to talk to you like a real programmer, right? And what's nice is that these plugins actually stack, right? Because they can always inspect the old error message. So when I was first testing this out, it also screamed all of the additional advice that the GHC error message index was giving me, all that stuff. Right, so that's sort of the list of examples. So what's next, essentially, right? So I have this idea that this interface, if available, would be a pretty nice test bed for error messages in the wild, right? You wouldn't need to develop a hypothesis and then, well, you would be able to develop a hypothesis, maybe this error message is better, and then test it on your students without ever having to say, compile GHC from source with a patch, right? But there's definitely other things that I'd like to explore before, committing to a proposal, namely, we'd like to rewrite errors from other phases, right? First years make other mistakes than type errors. They write case, but where the E is in the middle of the word, right? And then they get confused and they send you an email late at night. Additional information from the type checker environment to help the rewriters. What sorts of additional information would you want in scope is also kind of interesting. What sorts of hurdles will you have for adoption by library implementers, right? So say you did want to make a specific plugin for making lens errors more readable, right? Optics notwithstanding. What sorts of things would need to be available for the rewriter to actually be able to make that feasible? Then you've also got the simple question of, what is a simpler user error? What is a user error that students will find interesting? And that's just a wholly separate project, obviously, once you have such a plugin interface. And then just getting more and more examples, right? I can't think up many more weird ways of rephrasing your type error messages. There's screaming them, there's saying them like an anime character. I got that working the other night, and that was, useful, but, no. But so, yeah, more examples for testing the limits of the implementation as it currently stands. So, that's where I come to you guys. We've got a couple of forks. It's 100 lines of code. It's really quite small. The examples are much larger than the actual changes to GHC itself. Feel free to take a look. Tell me where I did something terribly wrong, and thank you very much.
Time for one question.
Oh, sorry about that.
Is this working? Yeah. So the question is, how do the users enable these plugins? Should they enable another plugin for every transitive library of your program that might need to enable custom error messages?
I mean, it depends. I mean, that sounds like a build system issue, right? I mean, more than anything else, right? Like, if somebody told me to do that, I'd be more worried about how I'm going to rewrite the Bazel and the make file than the plugin's capabilities. But in brief, I mean, yes, but I anticipate most of the benefit to someone who's developing anyways is those first order errors, right? The ones where you're depending on directly on a dependency and you've misused it somehow, and now it's angry at you and you don't know why, right? Yeah. I'm only here for today, so if you do want to talk to me about this, I'll be available the rest of the day, but make sure it's today. Yeah. Thanks a lot.
He's going to give us a lightning talk on fixed point programming.
All right, hello everyone. I'm Henry Blanchett, and I'll be talking about some joint work I'm doing with Michael Adams. So my research focus is on building tools to help programmers write correct and efficient programs. And today I'll be talking about our ideas for helping Haskell programmers write in fixed point oriented programs. So when you hear fixed point oriented here, think work queue style algorithms. And if that doesn't sound familiar, don't worry about it. These are a really common style of algorithms, and you've definitely seen them or even written them before. So let's walk through an example of how writing in this style works and how transformations over it works. So we'll start with a really simple example, graph distance. So we can define graph distance like this, where we have two relations. We have relations that define the edges in our graph and a relation for the distances in our graph. And then we have two inference rules that define how distance is defined in our graph, or how to infer distance. So we can get the distance over edges, and we can use this transitive looking rule to get the distance combining two distances. OK, so we've got the setup here. How would we write this directly in Haskell? Well, a naive implementation for computing all the distances in our graph could look like this. So don't worry about reading this code, by the way. I'm going to show a lot of code, but I'll highlight the important details. So In an algorithm like this, we have a few important components. We've got the initial distances, which we're going to initialize to infinity, except for the start, which is 0. We have the next edges to explore next, starting with the edges from the starting node. And then we have this loop that's going to process things in the items to visit next and push things onto there when we need to visit new items. And additionally, we have a check here to see if what we just visited actually did an update, which means we have to explore again, the nodes from there. Of course, though, this is just a naive implementation. It's not very efficient because we might have to visit nodes multiple times. So how could we make it more efficient? Well, we could use the classic, before I get to that, but this is a general scheme of a work queue algorithm. We've got a queue, we've got a loop that's popping and inserting off that queue, and we have some caches that are encoding intermediary results that we're computing. But like I said, this is a naive implementation, so how can we make it more efficient? Well, we could transform this implementation to something that looks like Dijkstra's algorithm. So for Dijkstra's algorithm, we're making it more efficient by having now a priority queue where we're ordering things by distance from the start to visit next. And then additionally, now we have this cache of visited nodes, so we don't have to revisit a node we've already seen. OK, so this is all well and good, but this is for a very simple problem, which was graph distance. So what do we have to do to handle something a little bit more complicated in our implementation here? Well, let's extend our graph distance now to something I'm going to call advanced graph distance, but not really graph distance exactly, but suspend your disbelief for now. So now we're adding a new kind of node in our graph, a multiply node. And how a multiply node works is it's got 2 input ports, and then the distance to a multiply node is the product of the distances to the input ports, encoded by the bottom rule there. And then the setup for that rule is in the bottom right. Just think about it conceptually. Don't worry about the details too much. So how would we implement now the same problem that we had before, but handling this new node? Well, we're going to have to add this new chunk here to handle that case. And you can see our implementation is growing. So you can imagine as well, if we had multiple kinds of nodes and say their rules interacted with each other, this could become quite tedious with lots of different cases that we have to handle. And additionally, if we want to make this a actually efficient implementation, we could extend it to look like this. And really don't worry about reading this, and it's a huge chunk of code here. But so the important parts here, though, are that we have a priority queue, which is ordering things so we visit them in the order of distance from the start. And we've got the same cache of visited nodes like in Dijkstra's, but now we also have this new cache of minimum distances among the input ports to the multiply nodes, so we don't have to recompute them pairwise when we update a distance to an input port. So in order to do this transformation, to make this more optimized implementation, we had to basically totally restructure the original implementation you saw way before. And that can be quite error-prone. It's also tedious. You have to handle many cases, maybe multiplicatively many, if the rules interact with each other. And additionally, it's quite difficult to do this properly. And if we wanted to use different optimizations, we would have to throw a lot of this work away to basically totally re-implement it. If we're encoding the data differently or encoding the relations differently, et cetera. So this is overall has some drawbacks to writing things directly in this style. So we have had this situation come up in other areas, though, before. An example would be parsers. So it's quite tedious and difficult to write parsers by hand sometimes, especially LR parsers. So we've developed tools, for example, parser generators, that take as input a nice specification of the grammar of your language, and then turn that into an efficient implementation of a parser for that grammar. So our idea is to do something similar for these styles of algorithms. So for the same kind of problem, we could instead write a description of the rules to compute graph distance, just like this, with these 2 rules, the distance from the start and the distance for an additional edge given a distance to the source of that edge. So just for reference, we're using this correspondence of the original mathematical relations that we saw before. We could extend it to advanced graph distance to look like this, just adding one more rule to find the distance to a multiply node. And yeah, so that's how you handle this example problem. But of course, you might be wondering, well, what else could this be useful for? I want to do more than just compute graph distances. So there's many other kinds of problems. that can be written in this work queue style of implementation, commonly are. And the common factors here are the shape of the computational dependencies. So in particular, if you have like an iterative shape of dependencies, that means you're going in a list shape. If it's recursive, then it's something like a tree. But for these ones, the shape of the computational dependencies really just depends on the type of optimizations and the encodings of data that you're using, which are going to change as you want to change the specification of your algorithm and the decisions about implementation. I'm going to go a bit quickly here because I'm running out of time, but I'm going to briefly introduce what I mean here by fixed point in fixed point-oriented programming. So we're working over a bounded semi-lattice of knowledge, and we're moving up this lattice, and we're using these rules to join our current knowledge with new knowledge as we infer it. So we're going to keep going up the lattice as much as we can using our rules, and then eventually we get to a point where we can't learn anymore. So that's like an abstract description of what I mean by these fixed point computations. Okay, so we're not the first project in the space. There's some other projects in this emerging paradigm, for example, Datalog, Datafund, and Flix. But in particular, these other projects are implementing as new languages, but our focus is on code generation for Haskell, and in particular, doing optimizations on that translation. So our current steps are moving from what we have currently implemented, which is as a interpreter, to a fully fledged code generator, implementing some case studies, and encoding optimizations into that translation. So like I said, we're still early in development, and we're here looking for feedback, use cases, and collaborators. And relating to HIW, for example, there's some fixed point computations in GHC, like strictness analysis. That would be good places to start for use cases. And if you're interested, you can check out our website or talk to us here at the conference. So thank you for your time, and I'm happy to take any questions.
Next speaker gets set up. Maybe one question?
So Joachim, as a
You can hear me okay? Sweet. All right, so I'm Philly McWin. I'm a Haskell consultant at Well-Typed, and I'm just talking about advancements in info table profiling. So this talk's all about info table profiling. I'm going to talk about what it is, what's an info table, since I won't assume that everyone knows that, and then I'll talk about what are we profiling when I say info table profiling, why does this profiling method matter, and how do we use it, and then I'll talk about these advancements that we're making. And this is a lightning talk, so I'm going to go as fast as I can. So what is it? Well, to talk about info tables, we have to talk about closures, and I'll just define a closure as a static or dynamic object that represents a value or computation in your program, and these closures are described by info tables. And an info table is a static data structure that describes the layout of a closure in a way that the garbage collector cares about. Is a good way to think of it. So just as a simple example, every constructor of an algebraic data type will have its own info table that describes how the garbage collector can traverse that object when it's collecting it.
So what is info-table profiling? It's a memory profiling technique where we're tracking allocations in the program according to the info tables that correspond to the closures being allocated. So like every info table will have a count of how many bytes have been allocated just based on the closures that reference those info tables. And then when we use this GHC flag that you may have heard about, f-info-table map, when that flag is enabled, the code that gets emitted for a module will include provenance data for each of the info tables that originate from that module, which that provenance data is basically just a best guess source location for that info table and the type of the closures that it describes. And then when we use this other flag, f-distinct constructor tables, every usage of a data constructor will be given its own info table. So in the end, if you use those two flags, you end up with info table profiling, you're able to attribute allocations to info tables, and then with those flags, source locations. And if you're using distinct constructor tables, you're getting allocations at every use site of a data constructor, which is very useful. And this is a diagram that I put together that sort of just shows everything that I just said. If you had a closure X, its header is going to reference an info table at some address P in your compiled code. And then in the info table map, that address P is actually going to map to the provenance data for those closures. So why does this matter? Well, this profiling method has very high information to overhead ratio. You don't need to use GHC's profiling mode, so none of your dependencies need to be profiled. You can just profile exactly what you want and get this information. And it has a negligible impact on program performance. So just having the info table map in your compiled code won't affect your program performance at all. And when you're profiling, you get a very true look at how your program is acting. The profiling instrumentation is not doing anything to how your program behaves. And then this profiling method has excellent tooling support with tools like event log to HTML, where you can just turn GHC event logs, which are basically program traces, into interactive profiles. And then GHC debug allows you to answer very low level and precise questions about how your program's memory is behaving. And for more on those tools, you can check out the Well-Typed YouTube channel, where we have a live streamed tutorial that I did for those tools, or our blog, where we're always talking about these tools. So how do we use info table profiling? You need several GHC flags and runtime system flags. First, the GHC flags you need to compile with at least f-info table map, and then if you want the distinct constructor tables, you should use that as well, and most people do. Then you need to enable RTS options, and then for GHC less than 9.4, if you're going to be emitting an event log, you need to link with the event log flag. And for runtime system flags, you need to actually say that you want to do a heap profile by info table using -hi, and then you need to emit the event log using -l. So I'll do a very quick lightning demo. I have a program here where it makes a lot of thunks. And so in the GHC options, I do RTS ops. I say f-info table map. And for this example, it doesn't really matter, but I can say distinct constructor tables as well. If I run this and just say I want an event log and I want a heap profile by info table, then the Thunkinator 3000 will start running. And it won't take too long, but every time that these numbers print, the thunks are being evaluated, and so we'll get a very spiky profile that shows a bunch of thunks and then them going away. So then with tools like event log to HTML, you just run that on the event log, and then that generates an HTML file that I can open. If I just open that HTML file, this is what the profile looks like. A bunch of thunks being allocated and then evaluated, but in the detailed tab, I can see that these are thunks. The type of these closures are thunks, and they are integers, and they're coming from the main module at exactly line 23, column 18 to 24. And if I go and look at line 23, column 18 to 24, I'm obviously doing, I have a lazy accumulator here, and that's exactly where that thunk is coming from. So, yeah. Another thing to note is that I'm using a GHC that has the info table map in here, so I'm getting a bunch of source locations and things for things that are coming from GHC libraries. So that's why these are here. But if you run that without a GHC with the info table map, that won't be there. Okay, that's the lightning demo. So what are these advancements? Well, producing the info table map used to be very inefficient, and on one particularly severe example, the flag caused whole compilation to take 130% longer and allocate 67% more memory. but this will be fixed in the next major release of GHC. And on the same example from above, whole compilation now only takes 13% longer and allocates only 10% more memory. And that's just an improvement that will be free to the users. And we're also working on making the binaries that contain the info table map smaller. And it gets especially large with distinct constructor tables because more info tables are being created and put into the info table map. But one observation is that the size of this info table map is often dominated by info tables that we don't necessarily care about for our profiling workflows. And so we're working on implementing features that allow users to filter exactly what tables get included in that info table map. And one of these flags that is now in GHC is this fno info table map with stack flag, which allows you to omit info tables for stack closures from the info table map. And often the info table map is dominated by info tables for stack closures because a lot of those get generated. And then also you can omit info tables that have defaulted provenance info. So if we can't figure out source location for these closures for an info table, then typically the source locations will get defaulted, but you can choose to omit those with this. And so just for example, I did some tests on the AGDA code base, but with info table map, it increased binary sizes for the AGDA code base by 36%, which is like 32 megabytes there. And then when you omit those tables with those flags, then the overhead goes down to 21%. So you go from 90 megabytes to 109 megabytes. So a small increase, but notable. And then, but when you use distinct constructor tables, the binary sizes are doubled on the AGDA code base. So distinct constructor tables introduces a lot of overhead. But we're changing distinct constructor tables to allow users to specify exactly which constructors this flag should apply to. So for example, you can say distinct constructor tables for only constructors that have this name, and that obviously erases the overhead of that flag and allows you to do very targeted profiling. And then also we're looking at adding, well, we've implemented a patch, but it's in progress, but we're working on doing distinct constructor tables per module, which causes only one info table to be generated for every usage of a data constructor in a module, which allows you to do like a sort of per module profiling. You can know how much this constructor is being allocated in this module, but you don't have to go so low as the exact source location of that usage. So yeah, it's just a more coarse-grained sort of distinct constructor tables profile. And that's all that I have, so thank you. Thanks to Hasura, who's the client that we've been working with that is funding this work on debugging information. And if you're interested in working with well-typed, please reach out to us. We'd love to work with you.
Any last questions?
From your description, it sounds like all of these this map is all allocated statically.
Yes.
Have you thought about doing it dynamically, so that you only sort of allocate an info table for a constructor that you actually hit?
I think mainly what I know about is one thing that's being considered is like out of band info table provenance, where like you distribute the info table map separately from the actual binaries, but I don't know about any efforts to do that dynamically. And just thinking about it, it's hard to imagine how that would work. But that's a great question. Ben probably, as always, Ben knows. Yeah.
Well, let's thank Finley again. This is the end of this.
Uh, can you say something just as a test? Uh, yeah, just keep talking. We're trying to observe the audio feedback. Okay. We can hear you, but the audio coming from your end is a little low. Do you mind like either moving closer to your microphone or speaking more loudly? Where's that coming from? Oh, I see. Gotcha. Echoing loudly enough through the room so where everyone in the audience can hear you. It's oh, uh, oh, okay. I'm sorry. We're talking amongst ourselves. I was just saying that we want to make sure that when your voice comes through the speakers, that it's loud enough for everyone to hear, and it's I think just barely loud enough right now. So if like during the talk, we need you to speak up, we'll let you know. Okay, perfect. All right. Are there any other audio tests you want to do? All right. I think that covers everything then. So I'll go ahead and sign off, and we'll see you in a little bit. All right. Bye.
Okay, you should be good. Okay, brilliant. Great, all right.
It's showing my code, but I also want to switch to my slides, which it's not showing.
Oh.
It's like it's only showing that specific window.
Mirror your screen, please. Mirror your screen. Maybe that
Yeah, mirror, if you mirror the screen instead of, all right, what else? Things good?
Yes.
All right, great. Okay, so first up, we're going to have Aaron Allen. This is the second session, by the way, Haskell Implementers Workshop. Welcome. Hope you all had a good lunch. Aaron Allen is going to be telling us about a GHC plugin for setting breakpoints. So thank you, Aaron.
Thanks,
Take it
Ben.
away.
Yeah, so my name's Aaron Allen. I work for a company called HEB, which is a popular supermarket chain in Texas, and some of our back-end services are written in Haskell. So I'm on the industrial side of things. And today I want to present a GHC plugin that I wrote to implement some breakpoint functionality. I found that having developer tooling facilitated by a plugin is sort of a sweet spot in the ecosystem for using plugins because you're not depending on it so much as far as your production code goes. So you can drop that dependency if the plugin is no longer maintained or something like that. So why make a plugin for breakpoints? So as you may know, there's a debugger built into GHCI that has presumably the ability to set breakpoints, but I've encountered a number of bugs with it, especially when it comes to concurrent programs like a web server. And I'll go ahead and demonstrate what I'm talking about with that. So here I have a simple program that's using concurrency to just fork a thread.
Can you make the text bigger?
Yes. So I'm just forking a thread here, and then I have a loop running in the main thread. So I will load this in GHCI, and I'm going to set a breakpoint on this line, line 13. And then I'll run the program. Okay, so a few things to notice here. The main thread is still running, even though I'm supposedly at a breakpoint. And also it didn't display this variable that I have bound. So that's missing, like it should be here alongside this result binding. And then furthermore, if I try to terminate this program, so I press Control C once, nothing happens. If I press Control C again, well, nothing happened again. Yeah, so right now it's in a bugged out state where I'm at the GHCI. Well, hang on. Actually, I need to continue. That's what I forgot to do. Okay, so now I've released the breakpoint, and now if I Control C, I have to Control C twice to get back to the GHCI prompt. However, the main thread is still running in the background, and the only way I found to kill it is to restart GHCI. And that's unfortunate because then I have to reload all my code as bytecode, and if you're working with a large application, that's a pain. And I can't just like re-execute the program like I can in this case because I'm not running a web server, but if I were running a web server, the port would be bound already, so I would be out of luck there. So in this case, I just have to quit and restart GHCI. So yeah, that's the main issues that I have with the built-in debugger. So what can we get with the plugin approach? Well, we don't have this issue with concurrency. And furthermore, I can pause execution of the program across all threads. And not having a reliance on the bytecode interpreter is nice because I don't have to load everything in as bytecode. If I'm testing something that involves multiple executables interacting in a concurrent way, I can compile a breakpoint into an executable and just run it without having multiple GHCIs running and using up a ton of memory. Also, your breakpoints are declared explicitly in the code rather than the sort of command line interface that GHCI has. So let's look at what that does. So I'll use this function called breakpoint.io and just insert that into my code. I will also turn on the plugin by passing this flag to GHC. So now if I run the program, so I get this output that says that I've hit a breakpoint. It gives you the location of the breakpoint, and then you'll get a list of all the bindings that are in scope at that point. And if you'll notice, the main thread isn't running in the background like it was before. It's actually stopped. So then after I press enter, execution continues as expected. Right, so the API for this plugin is pretty similar to debug.trace. If you're someone who uses tracing to debug your programs using the debug.trace module, this API is pretty similar in that you get these different variants of the functions. So I have breakpoint.io that is geared towards a monad with a monad.io instance. And you should use breakpoint.io if at all possible because it doesn't rely on unsafe perform IO at all. So there's no lazy IO thunks flying around. But there's also just the regular breakpoint function, which is a pure function that takes an argument. And there's also breakpoint M, which is for a monad that does not have a monad.io instance. And then there's another variant called query bars. So with this, instead of seeing, okay, so this behaves rather differently than breakpoint, the breakpoint function. In this case, it doesn't halt the execution of the program. It's just using a naive sort of waiting for standard in blocking on this thread. So In this case, I still see the main thread running, but what I do have is a prompt where I can enter variable names, and then I'll get this output. And the string is, in this case, it's generated lazily. So if you have a program where it's entering an infinite loop somehow where you've, say, bound a variable to itself, you can, it's helpful to identify that case because I can evaluate that specific variable and see like, okay, this is the variable where that's happening, rather than sort of blindly guessing. So yeah, query bars gives you that prompt, but you don't have some of the more magical features like pausing the runtime or some other things that I'm going to mention soon. There's also this exclude vars function where I can pass in a string containing the identifier that I don't want to appear in the output. So now I don't get any bindings for the breakpoint. Okay, moving on. So there's actually two different components to the plugin. It's both a renamer plugin as well as a type checker plugin. And the renamer portion of the plugin, it goes through and traverses the Haskell expression tree that results from renaming. And in so doing, it collects up identifiers and makes sure that they're scoped correctly. And whenever it encounters one of these API function calls, it replaces that with code which has access to a map containing all of those bindings in it. So that's how I'm able to display those bindings to the user. I'll show you what that code looks like. So it's a huge pain to do case analysis on the Haskell expression tree itself, because it's so massive. But it has a data instance that allows you to do some data generic traversal of it. So that's what I'm doing here. Like I have a case for each constructor that I'm interested in, and then I'm using the alternative instance of maybe T to try each of these cases. And I'm doing a top-down traversal so that I'm collecting variables up from the outermost scope and pushing them into the innermost scope. And the monad that I'm doing this in is based on reader T, which is really well suited to maintaining the scoping of variables in this case. And there's some interesting like quirks you have to be aware of. So like for a let binding, for example, like in the source code, you can put them in any order you'd like. However, after the renamer, they're ordered in such a way that any dependency between those let bindings is reflected in the order that they get put in the renamer output. So what I have to do is do a sort of dependency analysis on those and potentially put them in a different order based on whether a breakpoint expression appears in one of those bindings and it therefore references the other let bindings, thereby changing its dependency ordering. And I'm doing that by actually vendoring a function out of GHC, which is not exposed by the API, but it just goes and does a sort of graph analysis and identifies the strongly connected components in order to group those let bindings correctly. Yeah, but that's pretty much the renamer portion. So the other side of the plugin is the type checker plugin, and its purpose is to allow you to display any value regardless of if it has a show instance or not. And also, even if it's a unlifted value. So the mechanic behind this is that I have this type class. Actually, it's in. I have a type class called showLev, which is very similar to show, except it's levity polymorphic. And that just allows me to handle this case where I want to show unboxed types. So I have handwritten instances for an assortment of unboxed types. There's also code within the plugin to deal with unboxed types that I don't have instances for. So if we go ahead and look at that, sorry. Okay, so the main thing that's happening here is that I'm given a list of wanted constraints, and then what I want to do is check if any of those are for this showLev type class. And I have a special case for if it's an unlifted type, but in the lifted type case, I'm going to then want to have a show dictionary for that type. So in this showLev dict function, I'm making a new wanted constraint for the show class, and then I'm using that dictionary to pass into what I'm trying to build in order to satisfy the showLev constraint. And there's more to it than that, because if you have a type which, the outermost constructor does have a show instance, but then you have inner parts that don't have a show instance, then I want to show that outer part, but then default to a kind of phony dictionary for the inner type. And all the phony dictionary does is it just shows it prints the type of that value. And the way that I'm able to identify that that's the case is that if I get a wanted constraint for the show type class, I can inspect its provenance via the CT origin type. So occurrence of is a constructor of that type. And this happens whenever GHC emits a constraint due to a use of some class method. So like in this case, it would be the showLev method of the showLev type class. And then I can check that the name here is that showLev name. And if it is, then I can say that, oh, this show constraint originates from a use of showLev, in which case I want to emit a phony dictionary. And just to sort of demonstrate what that looks like. So if I remove this deriving show, so here I just get the name of the type, which is record, within angle brackets. And if I put it in a list, then that constructor also gets printed using its show instance. So the other aspect to this is the ability to pause the execution of the program. And there's a number of ways to do this. The way that I'm doing it currently is a little bit of a hack. So if you have a foreign function call which is marked unsafe, then the runtime will block until that call returns. And so I can kind of abuse that mechanic. So here I'm using the get char C function as an unsafe foreign function call. And that effectively blocks the runtime system awaiting input from the user. And interestingly, this didn't work prior to 9.2. Well, it did, however, while you were examining your breakpoint output, your computer would get really toasty because the CPU would be at max utilization. I don't know why, but it got fixed in 9.2, thankfully. So if it's not 9.2, then I just resort to this naive use of getLine. What I would like to do is use the RTS API to use the actual function that pauses the RTS, which GHC debug uses. But I've run into issues with my CI runners for Windows, specifically using that. So I've just been sticking with the old get char unsafe foreign function call for now. There's also this point about pausing timeouts. So if you're using thread delay, then the way that that's actually implemented is there's a priority queue that picks off callbacks for thread delays that are keyed at a certain point in time. And if you set a breakpoint and then release the breakpoint after a certain point, then those callbacks will all fire at once if enough time has elapsed. So what I'd like to be able to do is pause those timeouts somehow. And the way that I'm doing that is to actually manipulate that priority search queue, which is not exported by GHC. So to bring it into scope, I have to use the magic of template Haskell to break down the module barrier. So in here, what I do is, when I hit a breakpoint, I add a year to all of the entries in the priority search queue. So if you were blocked for more than a year, then it wouldn't work. But then after the breakpoint is released, I just subtract 1 year minus the amount of time that's elapsed. And I realized that this would break for 32-bit systems because they can only represent like 30 minutes worth of nanoseconds or whatever this is. But yeah, that's how I stop timeouts. What happened here? Okay. Yeah, so you can easily shoot yourself in the foot if you have more than one breakpoint that's referencing each other. That will result in an infinite program. And I've made it such that a binding doesn't have itself in scope, even though it technically is in scope. And that's just so, that foot gun is somewhat tamped down. But you do have to be careful with this. And that's where the exclude vars function can be useful if you are setting more than one breakpoint that are within each other's scopes. You can also have issues with polymorphic local bindings, like some where binding that's just a do statement without any type signature. It'll raise type errors about not having whatever, like monad IO instance. So you can solve that by either giving a type signature or using mono-local binds. Some ideas I have for developing this a bit further would be have a separate UI process, sort of like GHC debug brick, the brick interface that GHC debug has, so that you can more effectively use this with like brick-based applications that take control of the terminal, and furthermore utilizing the RTS API more to do some sort of heap analysis. All right, that's all I have.
Excellent. All right.
Okay. Yes, thank you, Aaron. I think we had a question from Etzko over here.
Thanks. You're a brave man. I have a question and a comment. A comment is I have a package called recover RTTI, which exports a function anything to string. Might be useful for you. It actually would be able to print your record, for example, even if there's no show instance. Might be useful. Question is, can you have conditional breakpoints?
Yeah, so I could, since it's just regular Haskell code, I could put it in like a when function call or some other control flow structure.
Right, but I typically might want to have, like, I'm not really sure where my code is breaking. I might need a whole bunch of breakpoints and then just sort of like in GHCI or some other way manipulate which ones I want to enable or disable.
Oh, no, that's not built in. But yeah, that's an idea that could possibly be implemented. And also I have tried that recover RTTI package, and I ran into an issue where when it tried to print a value, I think it was the vault type, like in a servant endpoint, it segfaulted. So I kind of backed off of that. Yeah.
It seems like there are really two ideas here. There's the breakpoint idea, and then there's the show anything idea, and they might actually be beneficial as distinct packages, even. If you can't.
Yeah, that's a good point.
All right, let's. I'm afraid that's all we have time for, comment-wise or question-wise. So let's have it again for a speaker. Welcome our next speaker. All right. So for the record, we're about 5 minutes behind at this point, maybe 6 or 7 minutes behind by the time we're done. So behind the program. Oh no. All right, maybe 15 minutes behind. We'll see.
Setting.
Okay. If worse comes to worse, we can just switch to another slightly top presenter and figure out a.
Yeah.
Okay.
That might be necessary. Let's see.
Right click on this. Oops.
Yeah, wait.
Right click on.
It doesn't.
Click.
But maybe I can just move it. Is it? Ah, there we have it.
Oh, yeah. All right.
Then I can't. Let's try.
All right, great. All right, Mark?
Yeah. I'm presenting a little bit about what we are doing with IHP. IHP's web framework, which we built at Digitally Induced since 2018, around that basically, and we open sourced it in 2020. And now it's actually quite a large community around IHP. And I just want to show a bit what we are doing basically and what we are using Haskell for. And just basically some things about IHP. IHP is like basically a batteries include web framework. So it's like, you can think of it like if you know Rails or Laravel or Django, it's like this, but with Haskell. And kind of combines the productivity of like Rails with the type safety of the Haskell, and kind of delivers like superpowers other frameworks cannot. Because in Rails you are very productive, but you have issues with like quality over like the lifecycle of the application, and with like IHP you have like all the power of Haskell basically. And IHP is like designed in a way that makes it easy for people to get like started with Haskell very easily. And so we basically lower the threshold of people getting started with Haskell so they can enjoy like the benefits without needing to learn about monads like the first hour they start using it. Here's a bit of
what other people say about IHP. So there's like a lot of kind of people say it's a great framework. So that's kind of there's quite a couple of people that are kind of very happy with it. Basically, IHP is really designed, and I think that's why a lot of people in the normal Haskell community are not sometimes aware about IHP. It's because it's like designed for people that, or basically people that are already experts in Haskell use Resort or Warp directly maybe, or Savant. But if you want to start out with Haskell and you have no idea about what you're doing, you might not know what database library to pick or what template library to pick. And with IHP, we kind of take off the decisions for the people, so they can just get something on the screen. And after they have like coded for a couple of days and they have something working, they might want to ask more questions. How is like this working? And understand a bit more about the structure. Because like when you learn Haskell, it's easy to get like the first functions and everything working, but then you maybe don't know how to like structure a larger program and everything. And IHP kind of takes a lot of like, or delivers like a standard structure kind of for a project. Actually IHP also is cool for Haskell experts. So it's not just for beginners. It actually scales very well for people that are experts too. So because it's in the end, it's just a wrapper around kind of a Warp and Postgres and a bit of IO and a bit of structure basically. The IHP community right now is like, we have like nearly 500 people in the Slack community. There's total like over 5,000 projects created. And at the moment there's like 250 in development IHP projects, what we can see from our telemetry basically. We actually have like quite a few projects now in production since it's launched. So here's a couple of companies that kind of use IHP actually in production. For example, Chemical Abstract Services, like US-based company. They are like modernizing an old IHP app, a legacy application that's been running like 50 years in production. And they're using IHP for that. Or RPV is like a residential like solar energy calculator. And actually, I learned earlier today that the Irish like Solar Energy Association is now like supporting that project. So someone's chatted on Slack that this happened. For example, I know there's like, because we consult on the project, there's like a project going on with BASF, which is like a large German gas company. For example, recently like MC Master University, they have like a thing where they teach programming to other students basically, and they build like the whole booking system with IHP, for example. There's a lot like more basically. We even got, I found this kind of funny, IHP was mentioned in like a German IT magazine next to like Java frameworks and all the like stuff we basically fight against. And this was kind of funny because and we don't do any press work, so this was even more funny to see that this kind of works. I also wanted to show some kind of case studies because it might, let's see if it works. Because people might wonder, okay, how do we get some company that only knows WordPress or something to use IHP, for example? And we have like a lot of like marketing documentation, for example, that looks kind of professional, and that helps like create trust for companies to use Haskell. So we have like these very, we have these G2 badges here, which is kind of easy to get for us because we just, we have a couple of reviews and then we get like these badges. It looks all very kind of professional. Then we have like quotes here and everything. And this like creates trust around Haskell and the ability that we, even if people have only heard about like WordPress and Django, that like Haskell is something they can work with because that's a problem we are dealing with. So we have a lot of like this kind of stuff. So that's just a thing. Otherwise, I just want to go a bit into the deals. We have like a PHP style feedback loops in IHP, for example. So we have like hot reloading. So when I did like learn programming in PHP, I was always going to like PHP scripts, make some edits, reload the page, and we have all this done with Haskell as well. Because a typically Haskell application you to manual restart, we don't have that in IHP. So we have like a very cool like development experience kind of. We have like a fully integrated dev environment using Nix. Basically, everything is like project local installed. every developer has the same everything basically, even like the Postgres database and everything. That's I just skipped that one. Yeah, we actually have web-based dev tooling. That a lot of people hate this at first, but it's actually quite cool because it's like inspired a bit by Smalltalk or the early Smalltalk tooling. But you can do everything you can do in IHP, you can do in code as well. So you don't actually need to do this. But I think people sometimes think like this is like web development for noobs, basically. If you have web-based dev tooling, but it's actually like very kind of productive. Here's some, but we can skip that. I think we can skip that as well. We have HSX, which is like JSX from React, but for Haskell basically. So TypeSafe had HTML templates, which is based on Blaze HTML, but it's like just type checked at compile time. We have great documentation, so we have like a lot of examples in documentation. We have like, we always use like specific examples instead of general examples. And we oftentimes like update the documentation when people ask, so that's like some stuff we follow, and I think that helps a lot people adopting IHP. And now we actually want to go to the live demo, so that's just the. I hope the timing fits. Is there a way I can do that with? Because I can't see my screen here. The problem is I can only see the maybe.
Oh dear. You may need to mirror your screen, I suspect.
Let's see.
6 minutes.
Yeah, we'll get this done. But how do I mirror it? So I have like both screens here.
I know what I guess that's
There it is.
And then,
but this is just where they are.
no, maybe
basically.
not. Okay.
Or maybe here.
Oh dear.
Is this CS? Is this one? No, probably not.
No, I don't think so. Yeah, no. Oh dear.
I mean, I can try if we can.
Yeah,
But this
that
would
might
be a
be
bit
the
terrible.
easiest option.
Maybe.
Yeah.
They can just. So. Okay. So if we want to do a new IHP project, we have this after you installed it, which is you just need to install like direnv and nix, and then you can install the IHP new package, which is like a project creator. You can use that command to create a new project. This will now it's not connected to the internet, so we have to fix it as well. Let's see if that works. Okay. So we create a new project. This takes a couple of seconds because it uses Nix to, like, we now actually use Nix Flakes with the latest version as well. So it just installs a couple of stuff from Nix Flakes, and then we have like Nix Flakes, and actually devenv based like development environment with a new project. So this now takes a moment, but it should go pretty fast after that. And yeah, in this development environment, we basically have everything to get started then. So that just takes a second. And you can already see it create a couple of files. And now if you go to the project, we can just hit devenv up and start this project. Now it opens the browser actually, but it opened it in the. So yeah, this is actually the dev environment here. So it's so it starts with the schema designer. So that's just a visual editor for the SQL stuff, but you can actually always split to this code editor or just edit the file directly. So but it's just a faster way to create SQL statements. And so we create, for example, let's say we create a table posts it automatically creates a primary key. You maybe give a post a title and a body, maybe some timestamps here, and it automatically like wires up like all the stuff we need, like database hooks and everything. Then we can it actually suggests a database migration as well. So we just run this one, and we have now set up our database schema for our blog application. We can now use the code generator here actually to just generate the controller, and then we go to the application. And now we have a very basic blog application running here, so we can just hello world and enter something. So right now we have not written any code. So that's one of the things which I mentioned. It's very easy to start. So and now what we are going to do is now we can just adjust our application here. So this is let's see. Oh yeah. 1 minute left. Oh yeah. Okay. So we have all the stuff generated here now, and for example, now we can go to our controller. So we have this controller here now, for example, and it has all the actions for our CRUD stuff in the application. And now if we want to, for example, add validation, we can just go here, for example, add validate field, title non-empty. Go to our application here, and if we now hit save, we get a validation error basically. Or if we want to change the body to be a text, so let's go to a new view, suppose new view, which is the generated code here. And we just change this to a text area, save it, go here, and we can see it automatically reloaded, and we have a text area field now. And that's the general idea. And then you go on with IHP and build stuff. And yeah, so that's, given the time constraints, that's I think the core idea. I think if you are interested, there's a lot of stuff coming to IHP soon, better deployment options, for example. We are working on right now, and yeah. And if you are interested, just check it out on ihp.digitalnews.com. Yeah, maybe give it a try if you are curious what we are doing with Haskell and the web framework space Yeah. Okay, any questions?
Great. Thank you. Let's thank Mark. All right. Yes, questions? Simon, okay.
So, I'm no expert on web frameworks, quite the opposite. But is it possible for you to describe in brief what's unusual or distinctive about the technical approach you're taking? How have you made your web framework to be the one that people are raving about in your quotes? What are the key insights I could take away about its design?
Yeah,
maybe.
I think there's probably multiple. I think one key insight is I think people just want to have type safety in their web applications. I think people really want that, and I think Haskell is too complicated. Like normal Haskell is too complicated to deliver that, in the sense that if you people want something they can, where they have a very low threshold to get started with, and low friction way to get started with. And all the existing web frameworks, for example, in the Haskell space have very high friction, and you need to always figure out, okay, Cabal or Stack or Nix or which database library I'm going to use and everything, and we've all taken care of that. I think people then get to enjoy the joy of Haskell, but in an easy way. And this makes people, I think, happy about that. Yeah.
But how did you get away without using, I don't know, Nix or Stack or database libraries or whatever? What made it possible for you to do something that they couldn't?
Yeah, we just are very opinionated, I think. And I think the other web frameworks in the Haskell space are not opinionated. So they always I think the core insight is other web frameworks, the Haskell space, are really designed for people that are already experts in Haskell. And IHP is particularly designed for people that have actually no idea what they're doing. And then we just make a lot of decisions upfront. So for example, a lot of people complained initially that you can't use IHP with Stack or Cabal because we only offer Nix-based and development environment, and that's it basically. And we also don't support MySQL, for example. We only have certain decisions that are designed. IHP is designed to be used in that way, and if you don't fit that pattern, you can't use IHP basically. And if you use it and follow the patterns, it will be like everything works very great together, basically. So it's because it's like it's kind of it's like that's why it's an integrated Haskell platform. It's like very like kind of integrated. Everything is wired together in a way that it delivers a great experience, kind of.
Great. All right. Let's thank Mark again. All right, great. Yes, so next we have Liao Jia, is that?
Yes.
Who's going to tell us about implementing deriving as a library. This is going to be interesting. Thank
Yeah.
you. Let's have it for our speaker.
So whereas usually you implement stuff by adding code, here I'm going to propose removing code from GHC. And in particular, I'm proposing to remove the deriving keyword from the language entirely. So what is deriving? Deriving is this thing that lets you construct instances of type classes. So in standard Haskell, deriving supports just a few type classes in the base library. And then there are some extensions that give you access to more type classes. And there are actually quite a lot of these extensions. And so what I'm saying is that, well, this is way too much. And there are many bad things about it. So first is that if you want to add yet another feature, you have to add a new extension, and then you have to change the compiler again. Also, like these extensions, like they really feel like they've been added like very incrementally. So in a way, if you already know how deriving works, then the next feature may make sense. But if you're like you're new to Haskell, then you have all of this stuff that you just get overwhelmed with. And finally, there's the fact that actually all of these features don't actually do what you want to do. And you run into odd limitations when you try to like derive some type classes in particular. Deriving via traversable is one example of things that just doesn't work. And so what I'm proposing is to simplify the language. It will make the compiler simpler to maintain, and also deriving actually easier to use. And so we can do much more with less. So how do we do this? By taking deriving out of the compiler, and instead we can implement it as a library. And I have implemented the little proof of concept, which is available on GitLab. So I'm going to just give a very brief overview of the kind of stuff you can do with it. So the starting point is to make instances first class. So the idea is to think about what is a type class. So we see a class, and one way to understand it is to know how it's compiled by GHC as a data type, actually. So when you define a class, it's actually some kind of record type in core. But, well, if it were just a record, you wouldn't need the class keyword. So it's a data type, but also there is some implicit parameter voodoo going on that in between the surface and core that lets you insert values of this data type. And so in particular, so one way to view this is that there is some kind of primitive that takes some constraint C in your some implicit context, and it turns it into an actual value that you can use. And then similarly, what is an instance? Well, if you an instance really, well, if a type class is a data type, then an instance is a value of data type, plus again some stuff related to this implicit parameter thing. Okay, and so what deriving does is to construct instances for you. But now that we see that instances are just value, we have a perfectly fine tool to construct values. It's called functional programming. well, the idea is that the voodoo is really nothing, right? Yeah, the idea is really to separate the voodoo. Because now the voodoo is like really simple. It's just this instance keyword, and then the rest of this information here is just a value, and so you make the language much simpler in that sense. So how do we derive values by functional programming? So to start, an example of deriving using a new type. So you wrap the int in some MIT, and then you may want to have EQ reuse the EQ instance for int. And so how this works with these first class instances? Well, if you have, now that EC is a data type, and you have this dict that lets you get access to some to the instance as just a value now, well, all you have to do to obtain an EC of MIT is to coerce it. And so using only this new primitive that we have for this first class instance variant of type classes. And now via is just coerce. So we can do deriving via without like adding anything to the language. To show another example, one is a generic deriving. And so whereas deriving via lets you coerce class dictionaries between coercible types. Here you are going to like inspect the structure of a data type, which usually has some sum of product, and you can use that to generate EC instances for most Haskell data type. And you can use deriving via to package this in a somewhat nice way. And so what I'm proposing now is that this instance here that was used for this generically new type that carries this generic EC instance now becomes just some value generic EC, which takes some EC dictionary on the underlying generic representation and constructs the dictionary for the type that you want the new EC instance for. And now once you have this generic EC, well, to derive this instance, you just have to, well, you just put the value here on the instance and you're done. So in particular, generic deriving subsumes the stock deriving, that is the standard Haskell deriving. And so now we see that deriving really is just a polymorphic value, some polymorphic class dictionary. So as I said, it's just functional programming. We already know how to do that. Here's another more fancy thing that you can do using this model. So, looking at, so we are going to need this variant of the functor class, where instead of mapping just functions, you map isomorphisms. And so it's like functor, it's like, actually it's more general than functor because, well, you can now map on the left of an arrow. And the other thing that we will need, notation we will need is this generic class, which gives you an isomorphism between some uniform representation and the generic type that you care about. Now, generic deriving for the IC class before, I had just put some ellipses, and now I'm showing you how we can actually implement that using these primitives. And so, again, you are given some dictionary on the generic representation, and all you need to, and now you want to turn it to an EQ of A. And so what you can do is that you can use the rep to turn the rep A into an A, and use the isomap to do that under the EQ. OK? And here we make a remark that actually this code barely depends on the fact that this is EC. It only uses the fact that EQ is an instance of this iso functor class. So we can generalize, right? And in particular, isofunctor can be derived generically, like functor. Like all you have to do is to map something, you pattern match on it, you reuse the same constructor on the right-hand side, and then you fold on the data, and then whenever you see a type variable occurrence, you just apply the isomorphism. Okay, so I'm not going to show the implementation, but so this can be done. So this is just a generalization of isomap to arbitrary generic type constructors F. And so now you generalize it by replacing isomap by this generic isomap, and you get this very general looking thing, but essentially I replace this EQ by some type variable C. And so now this works like for all classes that implement this isofunctor generically. And so this works for quite a lot of classes, but not all of them. So show and read don't have like these kind of this right kind of generic implementation to use this thing. All right, so it's quite powerful, but not all powerful. All right, so now to conclude, I've shown you what we can do by deriving, making deriving as a library. How do we do that? We use instances as first-class values. So there is this library on GitLab that I'm using. There is also a GRC proposal that tries to make this concrete syntax actually part of Haskell. For example, the library uses template Haskell instead of the instance equals syntax that I've shown in these slides. And we can do some neat things like generic deriving of generic deriving. Thank you.
All right. Thank you, Liao. Do we have any questions? Oh, yes, we do.
The dict primitive that you showed earlier, how tricky is it to implement this? Like that seems to be kind of like the thing that makes a lot of this possible. Like, do you have to do any?
Oh no, that's the easy part.
That's the easy part.
Yeah, the dict thing, you could think of it as like you declare one type class called dict of a data type called C, and its only method is a value of type C.
Oh, okay. So this is sort of like the reflection style
yes,
trick.
That's right.
I see. Thank you.
We could probably take one more quick question if that's.
So type classes and instances are not just values. There's also attached type families. Do you have any thought about that, or are they completely out of this plan?
I think for now, yeah, type families are out of this plan. I think maybe once we have dependent types, there might be a way, but yeah, at the moment I don't see a way.
Great. All right, let's thank Liao again.
Microsilicon, yes. How do I make it mirror? that you have here. Time make bootstrap test. Oh, well, I need to change directory. So first there, it compiled the runtime system, which is a combinator, interpreter, and memory allocator. And now it's, so when you do this, clone this, you get the combinators for the compiler so that you are not stuck there without the Haskell compiler. So now it's compiled once, and now it's compiling the second time, so you can compare if the bootstrapping succeeded and you have, they all produce the same thing. Yep, it worked. And it took just under 30 seconds to have the compiler recompile itself twice. And the combinator file itself is 136K, which is, I mean, the format is ridiculous. If you compress this file, it's down to 20K, so it's not that big. So, well, just like you, I've written the runtime system in C, but the compiler is written in Haskell, of course. In itself? Yeah. I mean, it's what you do with compilers. Okay, so let's to make it a little simpler, I'll make a compiler that has the combinators wrapped into oh no, what's this? It's not supposed to do that. Well, yeah, I mean, you can compile it with GHC if you want. Let me run the compiler this way. We want to run the file comb/mhs.comb. Okay, and so that's to run the compiler. And now the arguments to the compiler, we want to have look for some libraries, and let's compile an example. I can show you the example here, Kat. I mean, it looks kind of like Haskell. Okay, so now we only compiled it, and now we can run it. So it does something. Let's recompile the compiler again. I mean, it's so much fun to recompile the compiler. This time with an extra flag for the runtime system, so you can see what's going on. I mean, you don't see, you get the summary of statistics at the end. You can see the number of reductions and things like that. It was quite fun to do combinator reductions after not having done it for like 50 years or something. Whenever I did that last, maybe 45 years. So you can see here that it reduces 424 million reductions per second. So that means that it takes only like 10 machine instructions per combinator reduction, which I think is pretty good. It allocated 1.6 gigabytes. I mean, its allocation is high, of course, as it always is. And you can also see here that about 1 out of every 4 combinator reductions allocates a cell. So the memory management is all based on cells. A cell has 2 pointers. So it can represent an application node, which is all binary applications in combinators. And 1 bit is stolen so that you can tag some things not being applications, but they're actually combinators instead, or integers or what have you. If you just want to see what's going on while it's compiling. You can pass it. You can see that it's processing things. You can see how many milliseconds it takes to compile the different files. So this is compiling sort of everything. There's no nothing is, there's no separate compilation. Separate compilation would be very easy to implement because the nice thing about these combinator things is that you can serialize anything, and the runtime system has that built in. So if you compile a module, you can just serialize it out to file and then reuse that again. So I think I've shown you almost everything I wanted to show you. And why would anyone be interested in this? Well, not to compile code to run. But if you want to have a sort of a compiler that you can hack around in that is 6 files instead of I don't know how many there are in GHC, and without any ridiculous comments, then or any other comments for that matter. So if you really want to make it tight, you can combine the runtime system with the combinator code that I showed you. Then you get the binary that is about 200K, and if you run that through the executable compressor called UPX, you'll get the binary that is about 45K. So 45K is all you need for a Haskell compiler. Well, most people would say, this is not Haskell because I haven't implemented type classes yet. So okay, maybe 50K when I've implemented type classes. So I think you should not ask why this is so small. You should ask why other Haskell compilers are so big. Oh, I should make one. Can look in bin here. You can see that, yes, this is the one compiled by GHC. It is, I have a hard time reading it, 21 megabytes. All right, that's it.
Thank you, Leonard. All right, we have time for probably one question. Yes, we have. Javor?
Hey, that's very cool. I was wondering if you could say a little bit of how much of Haskell did you implement? So what is the micro Haskell so that we know how much we need to write the compiler?
Okay. So the big missing pieces are type classes and deriving. Then that means that there are some little bits. I haven't implemented list syntax with ... but that's sort of, and you can't have import lists on your importing. But I mean, there are little things that you can add that will not really make it any bigger. They would be very easy to add. So, yeah.
What part was the most fun, Leonard?
Hacking around in the C code. Oh, he asked what was the most fun part, and I said it's hacking around in the C code.
Quickly, just for a piece of historical verisimilitude, back in the early 90s, when GHC was just being born, what we spent our time doing was we'd release a new version of GHC, and then Leonard would release a new version of HPC, and it would be smaller and faster. And we would, so we would spend the next year toiling away, and then he'd do it again. It was always a very creative. So we just carry on this this tradition. But I don't really want to compete on compile time anymore.
I should point out that if you recompile the compiler with the binary generated by GHC, it takes 0.7 seconds to recompile the compiler.
All right, great. Thank you very much, Leonard. And for our last talk of this session, we have Junming Zhao, who has been working on MMTK. This is a remote presentation, so probably best to hold your questions till the end, I think. But Anyways, Junming, I think you're muted, but take it away.
Right. Can people hear me well? Can everyone see the screen share? What about now? Is it getting better?
Keep going, I'd say. Yeah, louder still. Okay, I think we may have fixed the problem on our end. Let's try again, Junming.
Can people hear me well?
Yep, excellent. Go on.
Okay, good. So hi everyone. I'm Junming, and today I'm gonna introduce the project of MTK GHC port, namely using MTK garbage collection in GHC. So the talk will have about 4 parts. Firstly, I'll briefly talk about the motivation of the project and what is MTK. And then we'll have a look at our MTK GHC port, including our development pathway, the current status and results. And then I'll talk about some of the challenges and key takeaway lessons behind the project. So first, people might be wondering, why are we interested in the port to use MTK? If GHC already has a sophisticated garbage collector? Well, first, the port can provide Haskell users with MTK GC algorithms, and it also can provide developers and researchers with an alternative, flexible, and credible platform to develop GC algorithms for Haskell. The port development also helps to bring cleaner and more modular structure to GHC runtime, and even if no one is using MTK at all. Here, I would like to emphasize that our port does not replace the current GHC storage manager, but it's rather an alternative to it. So what is MTK? MTK stands for Memory Management Toolkit. It is a research-oriented, general-purpose toolkit for different language implementers. It's led by Professor Steve Blackburn, and the team is based in the Australian National University. MTK was originally written in Java as part of the JAX RVM Java runtime, and it's now rewritten in Rust to be a generic library. MTK aims to provide a large selection of garbage collection algorithms that can be used by different languages with different infrastructures. While being language agnostic, MTK also aims to provide GC algorithms with high performance. So currently, MTK has a series of ongoing ports and a range of GC plans. And here, and for the rest of the talk, we'll use the term GC plan to refer to a particular memory management strategy. So our GHC port project started about a couple of years ago. We firstly started with refactoring some of the GHC runtime by identifying and removing some dependencies on the internal storage manager. The major dependencies we modified were about GHC block allocator, block descriptor structure, the per generation thread list, and weak pointer lists. Next, we started the port with a no-GC plan, which is a garbage collection plan that only does allocation using MTK without any collection of memory. Although no GC is kind of not a practical garbage collection, this phase served as the focus on finding out how we can use MTK for memory allocation in GHC. So this gives us the first key component of the port, that is where we teach GHC to know about MTK. For example, how to use MTK for allocation. So there were 2 sources of allocation that we touched in this phase. The first one being large objects and array allocation, which occurs in the runtime system. And the second one being allocation of small objects, which occurs in the generated mutator code. So we used the bump allocator, that is an allocation structure that both MTK and GHC use. In this way, we kept the same semantics of bump allocator as we have in the current GHC runtime without any major changes to the GHC code generator. So in the next phase, we added support for a non-moving plan. In our case, we use the non-moving IMIX plan. This introduced another key component of the port, that is to teach MTK to know about GHC. For example, how to do object scanning and weak pointer tracing. In our port, we wrote a fairly type-safe object model for GHC closures in Rust to support scanning. For the result, currently we can compile standard Haskell files with -mtk flag. Our modification allows the user to choose between either MTK or the GHC storage manager. We are able to use GHC to compile Cabal under MTK, and we managed to run the GHC test suite under MTK with majority of the tests passing. So to summarize, our development pathway thus far includes the refactoring phase, the Node.js phase, and the non-moving IMIX phase. And currently, we have turned our focus to the moving plan, where our main task is to introduce forwarding pointer mechanism in the port. And after that, we plan to introduce the generational GC, where we need to add write barrier in the port. And then we can have some comparisons between MTK and GHC internal storage manager that is also using generational GC, such that we can perform some evaluation measurement to get some concrete performance result. As for the challenges, one of the most interesting and perhaps difficult part of the implementation is weak pointer tracing, as the algorithm is quite subtle. And build system integration was also a difficulty in the project, as we have to integrate the compiling of Rust programs into the build tree. Another main difficulty for me was to decouple GHC's storage manager from the runtime system. There were dependencies, or in another word, abstraction leakage, which made it difficult to introduce generic modules like MTK. This issue is not specific to GHC, but exists in almost every language, which where components coupling and dependencies were designed to bring optimization. This also leads to a more general question idea behind MTK's philosophy and research purposes about software design. We usually think of balance between modularity and performance and components coupling, where MTK's goal is to have a generic memory management platform that can achieve both modularity and high performance. And MTK actually has demonstrated that this goal is achievable in the OpenJDK port, and currently developing GHC port will certainly contribute to the solution of a high performance generalized memory management framework. Lastly, I would like to thank Twig.io for the initial funding, Steve and ANU for their continuous support for the project, E for his help into MTK's internals and the entire MTK team, and Ben, who worked with me throughout the project. And thank you so much for listening. Here's a link and QR code to the project repo if you're interested.
Excellent. All right. Thank you very much, Junming. All right. So, do we have questions from the audience? Simon. All right.
So thank you for such a nice talk. I'm really enthusiastic about this project because garbage collection seems like quintessentially an example of something which is a quite complicated task with lots of different algorithms and tens of person years of development time that you could potentially share between languages and implementations, but which we tend to have bespoke garbage collectors for everything and just get Ben to implement a non-move. So it seems like a great plan. but it often stumbles on the details that you didn't say very much about, like that we use GHC's garbage collector to perform all sorts of sort of services that the rest of the implementation needs. You mentioned weak pointers is one. Another one is shorting out indirection nodes, which are created when we update thunks. Another is that when we've got a pointer to a fully evaluated thing, we then take the tag bits from the thing we're pointing to and put them at the tail end of the pointer. And I'm sure there are 3 or 4 other things that I'm not thinking of that it's hard for me to see how we can how you can be sure you can get all of these things going while still maintaining the abstraction barriers and modularity that you described for MMTK. So have you must have talked about this endlessly with Ben. Do you want to just say a bit more about some of those challenges?
I think for the details, so we put quite a bit of GHC specific code in the port. While this can be specific, the MTK code itself is language agnostic and it's modular, but we do need a per language port for to glue the parts to adapt to, I guess, different frameworks.
Yeah, to expand upon that. There we are. Yeah, to expand upon that a little bit, you certainly do need to have a very robust bit of code that is GHC specific. I mean, it is the majority of the work that we put in was in fact Rust code written to teach MMTK about the specifics of GHC's object layout, the fact that we have tag bits, the fact that there are this ability to do forwarding pointers. And rather for object interaction shortcutting. And all of these things, it turns out, actually can be fit pretty cleanly into MMTK's existing framework. That's not to say that all of them are. And there are certainly weak objects or something we're still sort of struggling with. Deadlock detection in particular, which is a rather tricky one, is something that we don't, I'm not, I think, fair to say neither of us are particularly happy with the design as it sits currently. But these are things that the MMTK team has been very eager to discuss with us, and this is a living project. So both sides are adapting to meet each other's needs.
So it's going to improve MMTK as well.
Yes, absolutely. Okay. Yeah, we've already been upstreaming. So and selector thunks. Yeah, that's right. But we did. Yes. Yeah. Selector thunk. Yeah. Yeah. So yeah, I think most of the functionality is actually there. There's a question of whether it is as cleanly implemented as you'd like, and that's another question. But functionally, I think it's actually quite good. It turns out that pointer tagging is actually quite important for correctness nowadays, as well as it's more than just an optimization. So you can't really get away without it.
Just a naive question. At the start of the day, there was a JavaScript backend to GHC. So presumably the V8 runtime doesn't have support for weak pointers and so on. So is there a completely different layer of translation happening for the JavaScript backend that lets it work in a totally foreign GHC than what is happening here with the GHC storage manager? Or is that just allowed to leak and you don't really care?
Sounds like a good question for Leute, if I'm not mistaken.
It's totally different, but we do struggle to implement some things. Like V8 does have weak pointers, but the GC weak pointer tracing algorithm is very unique to it. And we probably can't ask for specifics in the JavaScript runtime. We were thinking of introducing a different kind of weak pointer with slightly different semantics that allows it to run in the JavaScript runtime, but maybe there's an opportunity for WebAssembly, since currently the WebAssembly backend starts with CMM and works with it compiles the GHC garbage collector to WebAssembly and does its thing there, so that works the same. But the future of WebAssembly is that they add a managed runtime, and there I just sent to my teammates the idea that the lessons from MMTK we really should send to the WebAssembly team to see that if they can make WebAssembly GC suitable for Haskell. I hope we can work on that in the future. But it's complicated. But
if I'm not mistaken as well, you can probably compile MMTK to WebAssembly if I'm not, or to maybe within the script. And I'm not sure whether that's yeah. So. Well, yeah, you don't get to use the native garbage collector, but yeah. Great. One more. Oh, we're out of time. Yes, of course. All right. Apologies. All right. Thank you very much. Hear it again for Junming.
Besides Kudiri, who's going to tell us about his hack?
It's a nasty hack too. All right, so about 7 years ago, we had a client come up to us and he asked us, or they asked us, to debug some memory leak that they had, which we do regularly. I didn't think much of it. Which turned out to be the start of a very long and arduous journey figuring out what was going on. Which eventually led to a blog post called Sharing Space Leaks, Conduits and Friends, which I wrote 7 years ago, which I can only describe as utterly depressing. This made me kind of lose faith in Haskell in a while. Which is why I've titled this talk, A Workaround for One of the Most Important Problems in Haskell Today. Now, of course, I might be a bit biased, haven't thought so much about this problem. My colleagues might call me obsessed with it, but let's see. I do think it's an important problem. I have no solutions. I have a workaround, which is a hack. So this is as much as a call to action as anything else. So what is the problem? We have a lot of data in our programs that are not really data per such, but more things that drive computation. Right? They're not storing user information or things like this. They're telling our code what to do. And so a typical example is like a conduit, right, or a pipe or things like this, which is a data structure. You can think of it as a domain-specific language, which is describing incremental computation, right? For example, we might want to stream stuff from a database into a WebSocket, and we don't want to do this by first reading everything into memory and then streaming everything to the client. We want to do this row by row, right? And typically, one way to do this is to have an abstraction like this, which is a DSL. You describe your computation in this DSL, and then you have an interpreter of this DSL, which executes it, hopefully in constant memory, right, without growing everything in memory at once. So this is control data, right? This tells our code what to do, with the express goal of making sure that we can have streaming computations in constant memory, which is why it's all the more ironic that this client came to us and said, actually, we have a memory leak, and the very thing that we're leaking is this very abstraction intended for incremental computation, and a memory leak of type pipe in this case. Now, you never want to see this, right? Pipes should never be built up in memory, right? If you see a memory leak where you have a bunch of pipe in memory, then you already have a problem. So how might this arise? And I want to simplify hugely here, because this problem is quite subtle. So I'm going to consider sources. A source is like a conduit which only yields values, right? So this is almost like a list, right? We have a const constructor, which in this case is called yield, and then the nil constructor is done, and in this case, done also carries a result. And so, for example, yield from here is a conduit or a source that yields all the values from n down to 0. And then we have a very custom interpreter for this thing, which just runs the conduit. And what does it do? Every time it yields a number, it adds it to some accumulator. And then when it reaches yield, it just returns the accumulator. Right? Simple enough. Then I might have a simple test case, which constructs a conduit, which yields the values from 250,000 down to 0, executes it, right? Adds up all the numbers and prints it, or in fact, ignores it. This program runs in constant space, right? As expected. No problem so far. Now I'm going to have a minor variation on this program. I'm going to run an exception handler around this. And what is the exception handler doing? It runs the computation. If it returns a result, it just returns it. If an exception is thrown, it will just rerun it again. It's a bit contrived, but just to show the principle here. In this example, just to point out, the exception handler is never run. No exceptions are thrown, right? So that is not the problem. However, it doesn't know that in advance, right? So in order to be able to run the computation again, it needs to hold on a reference to this computation. So as the computation runs, retry holds on to this action. In this case, what is that action? Well, it's run source C. Therefore, by holding on to it, it's holding on to the conduit. Therefore, as we are running this conduit, GC can't collect the conduit as we're unfolding it, and therefore we're building it up into memory. Right, so this thing has a memory leak. And then you might say, okay, well, maybe let's just try to make sure that this conduit is allocated every single time that we run this action, right? Rather than allocating it up front. So you might try to move this in, right? Having the lead binding inside this retry thing here. And you will try it again, and you will find it makes no difference whatsoever. And okay, what can I do now? Okay, maybe let's turn it into a function, right? Maybe retry doesn't take an action, it takes a function that returns an action, maybe a function from unit, just to try and encourage this program to not allocate this thing up front, and you will find it makes no difference whatsoever, right? When you go down this path, you will lose your sanity very quick, right? Forget it. It's not going to happen, right? GHC does not give you tools to determine when something is allocated. There's passes in GHC for laziness that move stuff out of lambdas. There's passes like the state hack that moves things into lambdas. You have no control over this. Maybe we can come up with a language in which we do have control over that, but I think that's, as far as I'm concerned, not something I want to think about, because I think this is an assumption that's deeply ingrained in GHC that is quite difficult to change. And remember, even if you manage to do it in your library by very careful code, all of your upstream code that uses your library will also need to do it, right? This is not a solution. What you can do instead is before you pattern match on a conduit, you first duplicate the thunk. Now, dop.io is a primitive from a new package that we released last week. It's a fork from a very old package called ghc-dop, which is long since defunct. And what it does is it duplicates a thunk. Right? So it just makes a copy of it. Why does that help? Well, when you think about it, if we start evaluating this conduit, we reduce that thunk, right? It starts out as a thunk, right? We reduce it to weaker normal form. We then update the thing in memory, and we move to the next one, right? Then we reduce that to a weaker normal form, and so forth. So we're building up this chain of pointers from the head to the next one, to the next one, to the next one, right? That is the thing that we're building up as we're executing it. By pattern matching on it, by copying it first, the original thunk is left as a thunk in memory. It doesn't point to anything, right? Then we pattern match on the copied thunk. We reduce that to weaker normal form. But since this is a local copy, nothing else is retaining it, so it can be GC'd straight after, right? So by copying it before we pattern matching on it, we avoid constructing it in memory, right? In a way, and this is foreshadowing a little bit, we don't want this thunk to be updatable, right? This should be a non-updatable thunk, ideally. And by duplicating it, we can sort of do that in our code. Now, that's unpleasant to have to think about this sort of thing, and it gets worse. To show why, here's a minor variation on this, which is called a bidirectional source. And the point here is that we yield a value, and then to continue, we don't have the next source. We just have a function that takes some value from downstream and then gives you the next bidirectional source. And again, we might have the same yield from constructor. In this case, we don't need anything from downstream, so that new b prime parameter is unit. Okay, fine. Nothing changed. And then we might try to write our interpreter in the same way that we did before. Right? So in our go function, we first duplicate the thunk, and then in go prime, we pattern match on the duplicated thunk. Right? We just did the exact same thing that we did above. However, this code does not work. Why not? Well, if you think about it, when we are calling go again here, the thunk that we're duplicating is the application of the function to that unit argument. That is the thing that we're duplicating, which is not the thing that we should be duplicating, because that's not the thing that we were retaining in the first place. What we would like to do is evaluate that application, apply our function to unit, just enough that we get access to the underlying bidirectional source, and no further, then duplicate that, and then pattern match on it, right? We can do that by adding an additional interaction, right? We define some sort of box. Then our function is going to return a boxed bidirectional source, and then when we pattern match on it, we call our function apply unit, get the box out of it, get the underlying bidirectional source, duplicate that, and move on. Now, if you're thinking to yourself, this is awful, I completely agree with you, right? This is not nice. And it's very difficult to get right, because if there's some other thunk in the middle, we might be duplicating the wrong thing again, right? I told you I have no answers. I only have hacks. If I had answers, I would probably be, I think there's at least a PhD or two in here to properly solve this. Now, just in case you're thinking, well, maybe this is easier for conduits if we have conduits that, like functions that really depend on their input, right? Intuitively, that should be the case, because then GHG can't pre-allocate the next thing, right? So maybe we have an example here where we have a pipe, that's a more general thing. And what does it do? It waits for a character from upstream. If upstream tells it there's no more characters, then we're done. If upstream gives us a character, then we just count it and we move on. But GHG looks at this and says, well, actually, this expression here doesn't depend on anything. Let's move it up, right? So it moves it, it pre-allocates it before the await constructor. And so now what we have in memory, if we have this counter here that starts out as a thunk, we start executing it, right? We pattern match on it. We find out it's this await constructor, which points to a function, right? Which then in its closure points to a thunk, which is the next await constructor. Then we pattern match on this. So that also becomes an await constructor, which points to a function, which points to the next one, right? And so we get the same sort of chain of constructors. Before we had a yield pointing to a yield pointing to a yield. Now we have a yield pointing to a function, which in its closure points to a yield, right? But it's the same thing. And then, I mean, you might think, well, maybe if a character makes a difference, maybe if we do different things for different characters, then surely it can't do that anymore. So maybe we're only counting spaces, right? So if it's left, we're done. If it's a space, we count it. If it's not a space, then we don't count it. But GHG says, well, actually, no, this doesn't change anything at all. Both of these expressions can be pre-allocated. It moves both of them up, right? And now things get much, much worse. So for example, if I run this counter and I first feed it 1,000,000 spaces, then I do that again a second time and then a third time, and then I feed it 1,000,000 A's, and then I do that again and a second time, a third time, then the profile looks something like this. When we start feeding it the first 1,000,000 spaces, we're unfolding that part of the conduit, that path through the conduit. Then we count it again. Now the memory stays flat right here, right? Because this part of the conduit is already in memory. Then we start feeding it A's, so we get more memory allocated, a different path through this conduit. Then when we do that again, it stays flat, and then finally the whole program terminates, right? So we have 1.6 gigabytes of pipe in memory for this simple application. And it gets much worse, because every different permutation of spaces and non-spaces will explore a different path through this conduit. Right? So this thing has absolutely terrifying memory usage. Now we can fix it in the same way by having this box thing and duplicating before we pattern match, right? So the same solution works. Side note, you might try to write a smart constructor that every time that you construct a yield constructor, you insert a call to dup. So dup is the unsafe perform IO version of dup.io, right? Just a pure function of it. That doesn't work. Because when we're constructing this thing, we're now inserting a call to dup. Okay, so now if you interpret this thing, we would interpret that particular thunk, which is a call to dup, to weak at normal form. Okay, you get the copy, but now the original thing is in memory, is now updated. Right? So if you were to interpret that same conduit a second time, the very same constructor would now no longer have a call to dup around it. And so then the first time you're fine, but the next time you're not fine anymore. You could try to have the call to dup in the destructor, right, which is a bit better. That might work, but it's very dangerous, right? Because GHG will unpack this and inline things and move things around, and dup of something just looks like a pure expression to it. Maybe it gets shared by something, right? Not advisable. So it's much better to use dup.io or dup.st, where you are explicit about when and where you want to duplicate. OK. I want to show you a different application of the same idea, which is a bit more subtle, perhaps. Here's an example of a program which processes lists. Right? It processes a list of integers. What does it do? If the list is empty, it finishes. Otherwise, it drops 5 elements from this list. And you should think of this as modeling. We're processing some part of the list. Right? So this is a thunk. We pull 5 elements from this list. We do something with it, and then we're done. Right? So then we call perform minor GC. The idea is that this is all short-lived data. Right? We literally just allocated them because we just processed them. So we call perform minor GC to make sure that all that stuff is deallocated again. And we go and we move on to the rest of the list. OK? Then we have a small demo, which has 2 lists in it, left and right. Both have 5 elements in there. We process the left, and we process the right. OK. Let's look at what the heap does with this program. We start processing the left list. We have 5 elements, right? As we pull from this list one by one, our heap grows, the next element gets allocated, the next element gets allocated, and so forth. Then we call perform minor GC. All the stuff we literally just allocated, so it's short-lived. We deallocate everything, the heap goes down back to 0. Okay, looks good, as expected so far. Then we do the same thing for the right list, and we see the same pattern. Okay. Now I make one tiny change to this program. Instead of having 5 elements in these 2 lists, we have 20 elements in these 2 lists. Should be the same thing, right? So let's look. We run the program. We start processing the left list. 5 elements get allocated, deallocated, we're good. The next 5 allocated, deallocated. Next 5 allocated, deallocated. Next 5 allocated, deallocated. No surprises. Then we start processing the right list. We see 5 elements allocated, but no deallocation. Then the next 5, and the next 5, and the next 5, and no deallocation is happening at all. What is going on here? Why would this happen? Right? The only thing that I changed is how many elements are in these lists. It's crazy. Well, I said we expect this to be short-lived data, right? GHG uses a general generational garbage collector. We have multiple generations. And so all this stuff from these lists, we expect to be in the young generation. We just allocate it, perform an GC, deallocates it again. But this left and this right things are both allocated before we start processing. So when we start processing the left list, we have many calls to perform minor GC. At some point, GHG says, well, actually, this right list you had is not short-lived anymore. I consider it long-lived. I'm going to promote it to the old generation. Once that has happened, from this point forward, every moment, there's a link from the old generation to this new allocation, right, to this newly allocated chunks. And so minor GC cannot clean this up anymore. From this point forward, only major GC can clean up anything of these lists. That's awful. Now, this is, of course, a contrived example, but this is a distilled version of a real application. We have a big server for a client, which has a ton of live heap data. Occasionally, the server writes some stuff to disk, right? It does that by writing CBOR. How does the CBOR library work? It takes your data, it constructs an intermediate representation, which is basically controlled data, right? It's not data that we're interested in for the sake of the data. It's interested for the sake of driving our computation. It then writes the CBOR, and then this intermediate representation gets written to a binary representation to disk. Right? What is the CBOR intermediate representation for a pair? Well, it's the CBOR representation of the left part and the CBOR representation of the right part, just like here. Right? So then we start writing. These things may be big, and so at some point, that right part gets promoted to the old generation, and at this point, minor GC cannot clean up after us anymore, and so every single time that we need to do these GC, only major GC can clean up. But that's very expensive because this server has a ton of live data, none of which is changing. So what's the solution? Well, we can do the same thing. In a way, it's another instance of the same thing, right? We have control data that we don't want to be in memory, that we don't want to be retained. So same idea, same solution. What we can do is we duplicate the thunks before we process them. Right? Now we still have this right thunk in the old generation, but we don't care because it's not pointing to anything. It can live there, like it's one closure. Okay, nobody cares about that. We're then working with the duplicated thing. It lives in the young generation, and so everything is fine again. So one way that you might see, this is just a by the by, but one way that you might see that this is happening is that your live data is staying the same, even though your heap is growing. Right? So you can see that GC is not being able to clean up. So this is based on a new package called dub.io, which is forked from the old package, GHG-dub. We made a ton of fixes, and I say we, this is a lot of people in well-typed have helped with this. We've been thinking about this on and off for the last, 7 years. So there's been some GC issues fixed, CAF issues fixed. It now has a very extensive test suite, tested from 8.6 all the way out to 9.6. So I'm pretty sure that this is relatively stable. There's a focus on DAP.io, not DAP, although DAP is available, but I don't recommend it. Unlike the old package, it only supports shallow copying, right? So the old package also supported deep copying of graphs of objects. We don't support that at all. It's awful, right? I don't want to be writing code like this. This is not how I want to write Haskell, but it's better than nothing, right? I have no other solution for this kind of thing, right? Having a thing like a conduit in such a way that this sharing problem does not arise is very, very difficult. And it only happens in very small circumstances, right? And then finding out why it suddenly started happening is you can lose your sanity, right? So it's necessary, but it's not great. There is someone working on a better solution. Javier, he's a master's student. I'm supervising him. Unfortunately, he had made great progress in the beginning, and since then his employer made him far too busy, so he hasn't done much work on it since. But the idea is that you might mark some types as being non-updatable. Right, so something like a pipe or a CBOR intermediate representation, you know that you don't ever want a conduit in memory or the intermediate representation in memory. This is control data. It's not data. Right, so you could mark it as non-updatable. And then the idea would be that you change code generation so that you don't update those tongues. Now that's easy enough to do if it's monomorphic because we know what the type is and so we can generate different code. It gets hard for polymorphic functions, right? If I have some let binding, let x equals blah, 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 and that blah, 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 blah is of type A, now I don't know what kind of code I need to generate. And so there's some possibilities that you might do. You might at runtime check to see what the type is, but you can only do that after evaluation, at which point it has already been black holed, and so you don't have the original thunk anymore. So one naive solution, sort of a proof of concept, might be duplicate, evaluate, look at what the type is, and then replace it back, paste the original thunk back if you can. Just as a proof of concept that might actually work. But yeah, this is just research. There's no good solution here yet. Okay. That's all I have for you. If there's any questions, I'll be more than happy to answer.
Yeah, this is great. I wrote the original GHG library. It was 10 years ago. I just looked up. It was a first idea of me as a young PhD student. I had no idea what I was doing. The paper was horrible. It got rejected. I was devastated. It made it barely into a lightning talk at HIW. I just deprecated the library in favor of yours. So this great.
Thank you. By the way, your name is still as an author on the new package too. So.
Oh, cool.
Yeah.
That's very generous. Thanks. In terms of possible better solutions, GHG has the lifted kind for things that are called by name, and the unlifted kind for that are called by value. So could we just have a new kind for things that are called by name, and put it in the kind level, and the polymorphic problem disappear? And you wouldn't even generate the thunk allocation for things of that kind. Did somebody think about it?
Yeah, absolutely. We've been talking about this. Ben and I have been talking about it. We've been talking about it within Welltide. It would make a lot of sense to have a kind for this. You say the polymorphic problem disappears kind of by not allowing polymorphism.
Right, yeah, right? That's usually how you make problems with polymorphism disappear. But it's the same with the unlifted call by value kinds.
Yeah, but some people, in my daily work as a Haskell programmer, I never use unlifted types, and you need to have such a strong reason to use it precisely because you don't have the polymorphism, right? A ton of your abstractions no longer apply. So yeah, it's a very sensible idea. I just don't know whether it's practical enough, but maybe, yeah. It's possible, for example, lists, right? Many lists are driving computation, right? So maybe you can have a separate type of lists that do that, right? It's certainly something that's worth exploring, I agree.
It could be one tool in the toolbox.
Yes, for sure, yeah.
Any other questions?
Hello, thank you for the talk. This looks very similar to something we're running to in the JS backend, and we're kind of sweating back here. But this isn't really a question. As far as I understand it, this is some problem that has been existed since I guess for 10 years. I think we should name it. So what's a good name? Yeah, for the problem. And then the solution, whenever Javier comes up with it, is name of the problem, a solution, or something like that. So, or maybe ask Connell or ask Connor McBride, because he has punny names.
Oh, really?
Floating garbage.
Okay, so I will just repeat the first part. Simon said that there's a name for the major minor GC problem, and it's apparently floating garbage. I was not aware of this.
From what I remember, yeah.
All right, okay. It's good to know. Thank you. As for the name, I've been calling it the conduit problem for the last 7 years, which is probably not the best name, but that's where it started for me. So, but yeah, it would be good to have a way to refer to it.
I believe the systems term for something roughly equivalent is buffer bloat. I don't know why, it strongly reminds me of it.
Yeah.
Okay, one last question.
Would linear types help?
No. I mean, my PhD thesis is on uniqueness typing, so I'm not opposed to substructural types at all. I don't think it's a solution here. You would have to write your code in. If it's a solution in the sense that you avoid the problem, right? If you write your code in such a way that you consume everything linearly, then maybe you could set up something. But you want to write the code in the way that you want to write it, in a natural way, without having to worry about that, and it still work. So yeah, I think that's the short answer.
Okay, let's thank the speaker one more time and set up for the next talk.
I'm still carrying the microphone.
Way to inspect what GHC is doing, I believe.
Okay, thank you very much. My name is Ian Kim, and I'm from the Mercury Technologies. So today I'm talking about the GHC Spectre, the new plugin, which is I can call it like a show what you're doing right now, GHC plugin. Okay, so yeah, we Haskellers often, and also including all GHC developers, always confront the unexpected problem in very big complex Haskell projects. And we always ask questions, and why this type error happened, and what these dynamic link errors, and why these modules are recompiled, and also what is the bottleneck of my project build, how much memory GHC uses. We always have questions like that. And in fact, GHC knows it, right? So often, if you know, if you are GHC, and then I know why this type error happens and why this dynamic error happens because the configuration is wrong, or I know this module is bottleneck or something like that. But yeah, so I take one example, actually a real life example in a few months ago in our project. So we upgraded Nix packages, and then the build of our company's projects just got broken. And in the upper dependencies from this PostgreSQL simple. And then the error is just that there is no alternative either string instance. Yeah, it should not happen, right? I mean, it should not, there is no such alternative instance, right? But I know this instance was not there, from a long time ago, but why now it was broken? That was the question. And then in the end, when we look at the core expressions from that particular line, and then of course this alternative, the OR operator has the instance of this either string, and it refers to that core expressions. And if you look at the core expression, then yeah, that is from the transformer library 0.5.6.2. So transformer library has the often instance of this the alternative of either string. So that's what happens. So GHC already knows it. If you look at the internal state of the GHC, then we already have the answer. But just it is very obscure for us. So if we have some problem, then we should look into the GHC state. So because it is natural, because the answers to many questions are actually what GHC indeed need to know for the successful compilations. But the problem is that most of those information is ephemeral. It's just temporarily existent. Yeah, certainly we can dump information by GHC dedump or turning on some verbose loads, but that is not good for human health. Yeah, it's basically bad for your eyes. Yeah, it's like a fine needles in the haystacks, and it's built-in features, and that means it's limited and not customizable easily. Of course, we are GHC developers, so we can put some new features there with some flags, but first of all, it has a very slow development cycles for new features, and then also it inflates the number of the flags, so that's not really scalable solution anyway. So how about just a print debug print here and there in rebuild GHC? That's definitely not a solution, as you know. Yeah, needless to say, iteration cycle is very long. For example, in my project, if I just change the GHC code, and then if I just build my project, and then it usually takes 3 hours to just have the dependencies ready. Yeah, and so it's not readily available options with the big project. Even you can have a build script which can support the custom GHC anyway. So, but as you know, the GHC can plug in the code. So GHC has really excellent plug-in and hook mechanisms. So GHC is a really unique compiler in a sense. So GHC Spectre project is from that idea. So if I can make the GHC plugin that can command GHC to stop at the moment of the interest and ask queries. How about that? So, and then if I can ask that questions as we want, then why not make GHC answer the question in the form we want? So information we often want to have is usually in graphical form, right? So GHC has lots of graph structures, and why not just having that graphical form of the structure? And so that becomes okay. Then this project must be like first it should have some plugin component which can be just plugged into the GHC, but also it should have some kind of presentation layer which can show those results very beautiful form and then useful forms. So the GHC Spectre daemon is basically the companion process for user interactions and the visualization. Yeah. Okay. So the enabler for this is basically the driver plugin. So this is I often call it the mother of all plugins. So this is a relatively new plugin. I think it's originally introduced in 9.0 time, I think. And previously it's called the 9 flag plugin, and which was pretty limited at the time. But it's renamed to the driver plugin, and then it's actually changing the Haskell HSG environment as you want at the beginning of the GHC initialization. So it can govern the initialization procedure of the GHC, and it can orchestrate all the GHC plugins and hooks. That means basically, even you don't have any, plugin parameters for the others, like the many plugins we talked about today. Just you can actually load those things as you want by that driver plugin, in fact. So what GHC plugin, Spectre plugin does is basically it establishes a bidirectional socket communications channel to GHC Spectre daemon, the presentation layer, and during the GHC initialization, and installs breakpoints in every available plugins and then hook place. So that's the idea. And then also, recently the GHC pipeline code base is very tidied up. So, it's actually the fairly, the amusing experience to use those hooks, especially using the run page hooks. Okay, so the in a diagram is like this. So GHC applies on this target project, and then GHC plugin, GHC Spectre plugin can be installed with that just a simple two command line parameters, just f plugin the GHC Spectre, and then plugin package and the package, and then the GHC Spectre plugin as a driver plugin, it inserts the breakpoints at parse result, renamed result, splice run action, type check, core to core, everywhere. And then hooks, run phase hook, run meta hook, those things. Okay, and then as I said, it has this socket communication with the GHC Spectre daemon. And the daemon is actually organized as a kind of some abstract machine with the GHC, the GUI backend. So abstract coroutine machine, which is organized with the effective system with the free monad, is actually the backend independent. And then, in fact, the GUI backend can be replaced by any text-based UI or the web-based UI. But currently, the existing backend is right now just a native app GUI. Okay. So then user can interact with this GUI, and then you can just ask queries, or just get by default the GHC Spectre plugin also sends some information to the this daemon, and then you just get the result. Okay, so I will show the live demo with the actual real project Agda right now. Okay. So here I have some. In this GHC Spectre project, we already have the default Nix environment, and then okay, now my Agda setup is just like a so inside the Agda, what I added is just nothing but the sorry. Oops. Yeah, just added these two lines, just plugin GHC Spectre and plugin package, and then now I start the GHC Spectre. So it just shows the GUI daemon immediately, and then okay, I run cabal build Agda. Okay, it's not showing. So just to save time, I'm just disabling the vanilla library. Okay, then now it shows. Yeah, so all the information from the GHC, and actually, yeah, okay. So actually, the basic process ID or this kind of or this dynamic flag, and also the RTS information, they are often useful. So I just get it by default. And then also it fetches the graph of the modules. So from the GHC, just the module graph. And I have some, the graph layout library integrated into this. So it just shows the dependencies, and yeah. So and then so it's clustered, and then it actually shows the subgraphs. And as it compiles, it just shows the the current progress. So, and then of course, without go ahead.
What are the boxes in that part?
They are module. They are module. Yeah. What are those boxes? This is a module, but because the Agda has the 429 modules in this case, so actually showing everything is too much. So just it is clustered, and this is basically actually cluster of module, and showing that the most whatever the module which is imported most for and in that cluster. So it's kind of, and then by clicking it, I just show the what's inside in that cluster, and then of course without setting anything, you can actually see all the source code because GHC already knows the source code location, and when the compilation is done, probably I can just when the compilation is done, then yes. Oops. Yeah, so you can see the compilation. I'm sorry, it's a little.
I think simplifier ticks, or what are we?
Wait a minute. So I'm sorry. Yeah, I just exchanged again. So the screen size is just too small right now. Yeah, okay. Yeah. So, okay, as the, yeah, sorry. Yeah, so you can actually show the core graph of the project. So just as it compiles, actually, it knows that the AST of this Haskell file, and then it can actually analyze on live. And also, it shows just a timing of those modules. So actually, it is like this. So one module is really big. Yeah.
Is that modules or modules and passes on those modules?
Yeah, the modules, actually, the modules, just one module. The starting point of each module and then end point of each module for that compilation. And then if I just partition it, then can you see? Yep. So you can see that basically the dark blue is just the front end phase of the GHC. And then the light blue is basically after this core, the code generation phase. And the gray is the linking time. So you can show, this is just arbitrarily partitioned it, but you can actually give the more fine-grained partitioning like this. And also, you can also check what is the blocking. Okay, I can freeze. So in this case, this module is blocked by the Agda type checking positivity occurrence, and it blocks these two modules or something like that. So you can obtain who's blocking, who is blocked by this. And then, of course, you can make a graph out of that. So like, this is a whole blocking modules, most blocking modules in this project, something like that. So, and then you can partition it in terms of a number of blocking modules. So this is how it gathers information. But of course, you can also stop the GHC. So now I just pause the GHC, and GHC is really paused here. Yeah, and then it's just pause GHC in this here. So now it is paused in quote core phase. Okay. So then I just do the next. And then it is doing the quote core step after the demand analysis. And then it's doing the quote core after this constructed product result. So you can resume the session arbitrarily and start the session again arbitrarily. So as the breakpoint allows. So then, of course, you want to see what's inside this GHC, and then in this case, it's core. So I just want to, first of all, I can go to the source of this code. Yeah, now it's a code, the Agda type checking on code, and list cores. So it has this model has this cores, and I just check. I just click arbitrary cores and print like this. So in this way, you can just inspect what GHC is doing right now, one by one, and then compare each phase, and then how these expressions just change it. Yeah. So, and also another thing it does is basically this is a GUI program, and this is in a sense just GUI of GHC. So it can do anything. So this plugin allows. So recently, I actually added the support with the GHC debug. So here I'm just running the GHC debug brick. Okay. So now I started the new GHC debug session, and since GHC stopped, I just dump heap. So now GHC is now connected with the GHC debug at this arbitrary position, and I go into and then just pause the RTS right now. Then you can see the internal state of the GHC. Yeah. So this is just a GHC debug brick, and you can see the garbage collection route. From that route, you can just see the actual heap, the snapshot of the heap at the moment. But of course, this can be done better because this GHC debug is designed for the general RTS, but this is for the GHC RTS. So that means right now at this moment, actually I know what's the address of each object. So actually to find a certain object, in fact, you can just use that information from the GHC. Just we can just search it immediately. So right now I didn't implement it yet, but that's very easy to add. Or later on, yeah, this brig interface, GHC, the debugger brig interface can be integrated into this GHC Spectre. So this project has lots of different directions to grow. So this is the older live demo I can show. Yeah, so basically, as I said, this is kind of not a single-purpose project. I really want to make this as a kind of platform for everything the Haskellers wants to inspect inside the GHC. I think this is very good for the GHC developers, but also very good for all the Haskellers. As you know, it is very hard to imagine that the advanced Haskeller does not have interest inside what's going on in the GHC. So just knowing about what GHC does, just by seeing this visual information, it just helps us to be a better programmer, better Haskell programmer. So then we have lots of the interesting directions. So it can be improved in basic UI, of course, and then also here I didn't make many links. I just only show the source code location and source links showing the source from the start position. But actually I didn't show one thing. Yeah. So also you can actually make a breakpoint of the compilation. In fact, so that means. Yeah, for example, so in the source view, I just for example, I just check this. So I just set the breakpoint, and then even I just resume the sessions, and then when it compiles this agda utils tuple, it just breaks, and then you just start from examination. So by just a simple UI the elements, you can have lots of interesting things to do. Yeah. So back to original presentation. Yeah. So I think if I make lots of the linking informations around this this visual information, then we can also have lots of interesting analysis about the GHC. And right now the lot of weak point is just the backend inspection. This is because basically the GHC doesn't have many plugin points in the backend. So only I use the run phase hook, but that's already beginning of the backend, the code generation, and the end of the backend code generation. So I cannot see what's inside. So I think I just proposed probably we should have some STG2, like a core plugin, so STG2, STG plugin. Then if it is not used, it should not cost any runtime cost. So then we can use it as a plugin insertion point, and also it can be linked with any linker or the code gen inspection by the external pipeline monitoring, if we use LLVM or also the general linkers. And also GHC recently has this kind of multi-process semaphore support. So for this the multi-process GHC Java orchestration, we need to have support for that. And also GHCI, which is basically long-running stateful GHC compilation. That should be also supported. And also, as you see, the timing graph, if you know how the garbage collection is triggered, or when garbage collection is triggered, or those information, event log integration is also good to be added. Yeah, and actually this is being in progress. So and then we can also hooks more loggers, And then another very interesting project I can work on this is GHC I on the GHC itself. So when we stop it, we just invoke the new interactive GHC, run interactive HSC inside the GHC, but with the GHC library is loaded, and then just step inside the GHC with that current status. So that's also very interesting things. And also, as I said, the GHC debug can be also fully integrated with that. Yeah. So this is almost everything I prepared. Yeah. Okay.
Okay, and do we have any questions?
So it seems like there's a lot in here, and a lot of it seems fairly general. Like you focused on monitoring GHC, but it seems like there's kind of a general purpose monitoring story here, trying to come out as well. You have RTS monitoring and the ability to sort of break in the process at various points and report back state and visualize that state. Have you considered how you might take and generalize this to beyond GHC and there's something there?
Yeah, exactly. So I mean, basically I first want to have some really good tool for GHC itself. So and then, as I said, once this is really usable, then it can be used in any Haskell project. So and then basically librarize those components to the reusable things. It's an easy thing actually. So I first want to have something which is really useful for the GHC is a thing. And then I feel like right now it is a good time for comparing this with the other the available toolings. So for example, HLS and then the GHC debug. This is very complementary in a sense, right? HLS is basically towards the everyday development cycle, and it's basically more focused on the surface layers, like the Haskell language and then type checking. So and iterating as a long running sessions. But the GHC Spectre is more like a very deeply focused on the GHC pipeline itself. And I really want to see all the details of the GHC up to the final code, the binary code. And then GHC debugger shares also some territory, but the GHC debugger is more general RTS tooling. So as I said, for GHC specific RTS can be further developed for the GHC Spectre, but the general RTS tooling can be shared, and then we can use it as a kind of common ground. Yeah.
Oh, sorry.
Do we have any more questions? If not, I actually had a question, but there is one from the audience.
Hello. This looks great. Where can I use it or find it or get it? How do I get it on my system?
Oh yes, this is just open source. So first of all here, and then it is the package with the mix. So you can just first try, and then just feel free to have a contribution. Yeah.
So I had a quick question as well, which is in a way the opposite of Ben's. So have you, Ben asked, what about generalizing that to other projects? I was kind of wondering which passes of GHC are particularly good to have a specialized custom view. Like I could imagine, say, the type checker. Like you kind of showed, this seems really good if I'm trying to debug my build system or something, see what depends on what. What kind of visualizations have you thought of? Like if I have a type error and want to understand it, right? There's all kinds of things I can imagine.
Yeah. First of all, we should have a very good AST visualizer. So core, STG, also the Haskell HS. So yeah, that's the first thing. And then of course, the information in especially name can be interlinked together. That's very helpful for navigating what's going on inside the GHC. And then of course, GHC has lots of the internal things. So definitely we can have specialized view for that. Yeah.
Great. Let's thank the speaker one more time. And next. tell us about, well, execution domains in GHC. I'm looking forward to finding out what that is.
Yeah. So yes, my name is Ben. I work on GHC at Well-Typed as compiler engineer, and I have been thinking about this problem off and on for almost as long as I've been working on GHC, and that is because, as we all know, computers are getting larger and larger, especially on a server, in a server sort of environment, where you can have easily hundreds, if not thousands of cores on a machine now, hundreds, if not hundreds of gigabytes, if not terabytes of memory, and ultimately, server applications needs are growing, for throughput and also for latency are getting more and more stringent. So you might think, well, you have hundreds of cores, you have server applications whose requests are fairly independent of one another. You're typically servicing many requests, and but they're not doing a whole lot of collaboration in many applications across requests. So you might think, well, this is an ideal sort of setup, right? We should be able to scale quite well in this sort of situation, but there is a slight issue, and that is that often, in many cases, server applications also have a considerable heap requirement nowadays. So it's not, I know of more than a few commercial users of Haskell who also have hundreds of gigabytes of live data on their heap. And this actually ends up being quite a challenge for an implementation of a managed garbage collected language like GHC Haskell. And GHC, I think, actually has some great benefits. Our immutability, I think, is actually a great asset in dealing with this case, or at least it could be, as we will see later in this talk. And my goal today is to convince you that there's actually a really relatively straightforward idea that we can borrow from other languages. Erlang and OCaml come to mind here, that I think sort of play to Haskell's strengths and make it applicable in a wide variety of areas where we currently sort of struggle. And so that is my goal today. So let's say I write a server application, and I use all of the wonderful tools that GHC allows to provides us with to write high-performance, concurrent, and parallel applications, and I do sort of naively just run it, right? I have my server here, and I run it, and that's going to give rise to an execution environment that looks something like this, right? We have one CPU, because I didn't enable any parallelism. It has one or more green threads, probably more, because I wrote my program specifically with parallelism in mind. They're all serviced by a nursery and some multi-generational heap. Of course, I'm not going to see any parallelism in practice until I actually tell GHC to use all of those cores on my machine, and at which point I'm going to have multiple cores, now all working on distinct sets of Haskell green threads, each serviced by a small nursery. Of course, even now I'm still not going to see, I have N64 now, and that's not actually going to be anywhere near the sort of speed up I'm going to get, even in a nearly ideal application with, plenty of parallelism, because like many languages, GHC's garbage collector requires a bit of tuning to really get any sort of real speed up. And so, if I increase my nursery size, as I've done here, right now these nursery things are a bit wider, indicating that we've actually increased the amount of memory available to each core to allocate into, and consequently we have to do less synchronization, right? GC is going to be often become more efficient, and I'm going to begin to start to see the sort of speed ups that I might hope for in my application. However, we still have a lot of work to go long distance to cover before we get anywhere near the 64x speed up that we might sort of hope for in an ideal case. And we have to do things like tell GHC to respect the NUMA, the memory topology, right? Make sure that we locate each nursery close to the CPU that is going to be using it. We have to ensure that we use the GHC's now non-moving garbage collector to ensure that there aren't long durations of time where where we cannot serve requests at all, avoiding latencies from major collections. And we might even need to start making modifications to our source program, right? Leveraging techniques like this paper from Ed Yang from many years ago now, to tell the garbage collector something about the structure of the heap and how we expect object lifetimes to relate to one another. And again, increasing sort of the efficiency of garbage collection. And so all of these approaches that we've seen here are really all working around this sort of fundamental fact that, well, it looks like we have lots of parallelism here, right? We have lots of independent requests. They all are actually tied to a single shared resource, and that is the runtime system, right? And we have put lots, Simon Marlowe can certainly speak to this, and I've put in plenty of work myself in trying to make the runtime system more scalable. But this sort of work is an endless sink of time, and it often comes with diminishing returns. And at some point, the fact that there is only one runtime system, all of these threads are tied together under the one runtime to rule them all, is really inevitably going to be a bottleneck, I would argue. And moreover, we have the fundamental problem of different components of a program often differ in their optimal scheduling and GC policies, right? So if we were to really start to address that issue, we really need to start thinking more of our program as a distributed system, right? You need to start thinking about things like message passing and how do we isolate various portions of our application from one another. Start thinking about them as really distinct processes. And we have great tools in Haskell to deal with problems like this, right? The Cloud Haskell paper comes to mind, sort of building upon the Erlang heritage. But unfortunately, for many applications, especially a few that I can sort of have in mind from our commercial users, it is quite difficult to sort of render the application as a distributed system in a multi-process setting because you have, again, this hundreds of gigabytes of data in memory that you need to somehow distribute across the many processes that are now serving your application. And so we might not need multiple machines. We don't necessarily want to distribute across computers, but we do want to have these threads of our application running in separate processes. But we certainly don't want to duplicate the entire 100 gigabyte data set that we're querying in our program across each of those processes. And this is quite bad, especially because memory footprint is often the dominant factor in determining the hardware requirements of hosting a service in an industrial setting. So there are actually commercial users who have started doing real headstands to try to work around this. Whereas I think with a relatively small and I think not that hard to implement feature, we could actually make this status quo considerably easier to work with. And this idea that I'm suggesting here is sort of borrowing from the what multi-core OCaml calls a domain. And I think it's slight differences here, but nevertheless, I'm going to borrow the terminology and define it as a pair of local heap coupled with some policies, right? Essentially, we can think of a domain as the runtime system as we think of it now, but perhaps sharing the various aspects, the block allocator, right? The various bits that that don't pose a severe hazard to scaling. In particular, the idea here was we want to be able to allow multiple heaps within a single process, allow sharing of data between them in some global heap structure that can be explicitly evacuated or promoted into, and then allow communication between these domains by way of message passing. And this allows us, if we are careful, to ensure that we do not allow inter-domain references. We should be able to allow GC of these independent heaps in a relatively, independently. So how might this look in Haskell? Well, I would propose sort of an interface that might look something like this, right? We have a fork operation where, very similar to fork IO, and we're leveraging many of the pieces that we have already seen in the distributed Haskell setting. Static pointer, for instance. We allow to ensure that we can easily safely pass the action that we are spawning across the domain boundary. We allow again, channels in a Cloud Haskell-ish setting, allowing data to be of a particular flavor. Again, immutable data. We're going to leverage compact normal forms as the representation of our messages. And we are going to allow sharing of channels and this sort of shareable data across these channels across the domain boundaries. Likewise, we have an operation to globalize data onto the global heap and allow such references to be shared across many domains. So I think we're actually not that far from being able to implement this sort of approach. Here, there are a few tricky cases, but I believe that this is something that actually is quite viable. And to recap, I think that if there is a lot of potential benefit to be had in this sort of generalization of GHC's runtime system, and I hope others will find this idea as exciting as I do, and we really could use your help in realizing it. So if you are interested in sort of seeing this idea come to fruition and you have time to implement it, then please do be in touch. Thank you very much. I apologize for being a little bit over.
Yes, I've thought along similar lines, and I kind of got stuck on the CAF issue. So how far have you got with thinking about CAFs?
So I think the CAF issue is indeed a tricky one. And your local heaps paper, I think, explores many of the ideas here. So I think really the easiest approach, which I think is actually, if you really start thinking about this as a distributed program, the CAF, you can localize CAFs is my first thought, and ensure that things that you have to have enough control over the manipulations that the compilation to ensure that things you really want to avoid being that you need to share are not turned into CAFs. And that is a tricky problem. As we see in EDSCO's talk, controlling when things are allocated and which things are floated to the top level is hard. But that's a problem I think we need to address either way.
Or you could sort of virtualize CAFs and have a CAF table per.
You could. That's absolutely right. Yes, that is certainly another approach. I'm not sure, that's sort of the trade-offs that I'm leaving as exercises to the reader, rather unfairly, but 7-minute talk, 10 I guess now. EDSCO, over.
I'm not sure I completely understood the requirements of immutability on the global heap. Like, so typically a big server might have a ton of data, which is mostly unchanging, but not totally unchanging. So how does that work?
Yes. So, well, the requirement is the rationale for that requirement is that, again, we want to ensure that no data is that we can safely collect each individual domains heap without worrying about references from the global heap or others. Now, how do you actually work under that restriction of immutability in the global heap? That is as well that currently, when you're working with a distributed system or in this sort of distributed mindset, you typically need to start designing your application around the restrictions of that model. This is one of those restrictions, right? And so, indeed, if you do have a occasional update, you might need some largely immutable data that is occasionally changed, then you will need to sort out a data structure, a representation that will allow you to perform those updates while avoiding doing too much work in promoting too much data into the. We can talk about how that might look, but yeah, that's right.
Okay, let's thank Ben one more time, and next is Shane.
So I had my first Haskell job, and we used property-based testing, and some people ran 100 tests, and some people ran 1,000 tests, and some people ran 10,000 tests, and I was like, how many is enough, right? So I ended up asking my friend Chris Smith, and he said, the way to find it out is to turn on HPC, and then you go look at the pretty colors, and you figure out, like, did your code get covered? And then I had to go play around with my Cabal properties and turn on HPC or turn it off. And I was like, what would be really great is like if the computer just did this for me, right? Like, can I just get the computer to do it for me? And so about 6 weeks later of like learning all kinds of things, playing with event log, doing all kinds of other things that did not actually work out, it turns out that HPC at runtime can reach into the RTS and just get the counts of all of the regions that have been executed. So HPC, what it really does is each of your regions inside there get one little integer. And so my choice for answering the question of how many tests is enough is I just keep running as long as code coverage increases. And so that was like each of these little regions inside each of these little regions that you get back from HPC. This is my whole library. It is almost nothing. It's great. And really, the whole exciting part is that you call examine ticks here, and that gives you back this list, an IO list of a bunch of integers. And if more of them have become non-zero than the last test, then keep running tests. And so that's pretty much it. Wasn't that a great short talk? Yeah. Okay. Any questions? Joachim?
So if your tests are randomly produced just because it didn't bump in one iteration, doesn't mean there isn't a good chance that maybe the second test after that increases. So do you really just stop when it doesn't increase once, or do you like keep running for like another 1% extra and
Yes. In fact, the grab until n same, you can pass it however many you want. And I decided 40, just kind of like trying it out. 40 seemed to be fine.
I would recommend 42.
Oh, absolutely. No, you're right. That's a good choice. Yeah. Let's go.
So I'm curious, what in your examples, what's the right number?
What's the right number?
Yeah, I mean, just in practice, like when you start doing this, are you running 10 tests, 100, a million? What's actually happening?
So it turns out that I supported 3 different things because I wanted to compare them. So I've got Hedgehog, and I've got Lean Check, and I've got Quick Check in here. And you can tell that I had a lot of extra fun with Quick Check because I had snippy comments in there. And Hedgehog was okay. And one of the things I found interesting was like how quickly does it converge? What is kind of like you've got as much coverage as it's going to get? Lean Check got there like super fast. And so I've been using Lean Check for a lot of my stuff since then. Was that kind of the question you were asking, or like how many was enough, or?
No, I mean, you're saying I don't want to pick a number, right? I'm just going to run it until, but then there's an implicit number, right? Like the number that you end up with. So I'm just curious what that number is.
I think it's going to depend on your code base.
Yeah, of course it's going to depend, but maybe in yours, I mean, just a ballpark. I mean, I've just, in your examples, because I could imagine maybe it keeps running forever, or maybe it converges very quickly, and if it converges very quickly, then is that, I'm just curious.
I don't have a good answer, but you know what? I will find out, because now I'm curious too.
You didn't run examples?
Well, I mean, I ran a bunch of examples, and so
So how many tests did it run on those examples? Give me a number, man.
Okay, let me think. I think it was about 60 or 70 was actually how many random tests. But it also depended on like what you're using to generate, right? So like Lean Check is enumerative, and like Quick Check is just whatever, right? So it just depends on how it gets generated.
You said you compared at least 3 different property testing libraries. Did they actually converge to roughly the same, or comparable coverage results?
They did.
Okay, that's good.
Quick Check took a long time to get there.
Yeah.
And Lean Check was really fast,
yeah.
and Hedgehog.
But they're the same sort of. They covered the program equally.
Almost every time.
Good.
Yeah.
It's reassuring.
Any other questions?
Is it available on package?
Oh, absolutely. Yeah, kudzu. Kudzu will cover all of your bugs.
Okay, let's thank the speaker and then
All right.
we're done.
Real quick before we depart, I want to give a special round of thanks to the AV team for their absolutely heroic efforts to make this work. This would not have been possible without them doing some last-minute bug fixes and figuring out what's going on in everyone's laptop setup. So huge round of appreciation to them for